Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the ancient story of Mars and Earth, two worlds born from the same cosmic dust, yet destined for such different fates. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. In the beginning, there are two spheres of molten rock cooling in the darkness of a young solar system. Mars and Earth spin in their separate orbits, separated by tens of millions of miles of empty space, but they share the same birthday 4.5 billion years ago, when the solar system itself was nothing more than a swirling disk of gas and stone particles. The same iron that would one day flow through Earth's liquid core also settles into Mars's gradually solidifying heart. The same silicon that would build Earth's first continental masses also crystallizes slowly beneath Mars's cooling surface, grain by grain, crystal by crystal. They are planetary twins in the truest sense, these two worlds, forged in the same stellar nursery from the same primordial materials. The asteroid belt that stretches between them holds the leftover debris from their violent creation, chunks of metal and stone that still remember the exact temperature and pressure conditions of that primordial moment when solid matter first began to condense from the solar nebula. Scientists studying meteorites that originated from Mars, ejected by massive asteroid impacts and eventually captured by Earth's gravity after journeying through space for millions of years, discover that Martian rocks contain the same fundamental isotopic signatures as Earth's oldest geological formations. The elements that make up both planets were cooked in the nuclear furnaces of the same dying stars, scattered across interstellar space by the same ancient supernovae, and swept together into this corner of the galaxy by the same gravitational dance that shaped our entire solar system. Yet even in their shared infancy, subtle differences begin to emerge with profound consequences. Mars forms as the smaller sibling, gathering only approximately half of Earth's total mass during the chaotic period of planetary accretion. This seemingly minor distinction, a difference measured in fundamental gravitational strength, will determine everything that follows over the next 4.5 billion years, the thickness and composition of their atmospheres, the strength and longevity of their magnetic fields, the duration of their geological activity, and ultimately, their capacity to sustain liquid water and perhaps life itself. The universe, it seems, pays extraordinarily careful attention to planetary size and mass, with consequences that ripple across geological time. Both worlds begin their existence as hellish furnaces, where no solid surface can maintain stability for long. Magma oceans hundreds of kilometers deep cover their surfaces, while the cosmic bombardment known as the Late Heavy Bombardment continues to rain metallic asteroids and icy comets down upon their molten exteriors. The young sun, still settling into its nuclear rhythm, burns with dangerous and unstable intensity, sending waves of high-energy radiation across the inner solar system. In this chaotic and violent environment, Mars and Earth begin the slow, methodical process of planetary differentiation, heavy elements like iron and nickel sinking gradually toward their cores under the influence of gravity, while lighter silicate materials rise toward the surface to form the first tentative, constantly reshaping crustal layers. The iron within both planets settles into liquid cores that will drive their magnetic fields, but Mars's smaller size means its interior cools more rapidly than Earth's more massive heart. The Martian core begins its transition from liquid to solid much sooner than Earth's, setting in motion a cascade of geological and atmospheric consequences that will unfold over billions of years with mathematical precision. Only much later, after decades of planetary exploration and computer modeling, will scientists realize that this early cooling process holds the crucial key to understanding why one world eventually thrives with abundant liquid water and complex life, while the other gradually grows silent and cold. Ancient zircon crystals, among the oldest minerals that can be found on either planet's surface, preserve precise measurements of temperature and pressure from these earliest epochs of planetary formation. Each crystal forms a microscopic time capsule, smaller than a single grain of sand, yet capable of storing detailed geochemical information across entire geological eons without degradation. The mystery embedded within their precisely ordered crystal lattices is both elegant and profound. How did two nearly identical worlds, born from exactly the same materials and warmed by the same nuclear furnace of a star, evolve along such radically different evolutionary paths over deep time? The irony becomes apparent when written in stone and preserved in mineral form. Mars, named by ancient civilizations for their god of war and conflict, will ultimately prove to be the more geologically peaceful planet in terms of surface activity. Its ancient terrain will remain largely unchanged for billions of years, preserving impact craters and geological formations like a vast planetary museum of early solar system history. Earth, eventually crowned with abundant life and flowing water, will remain the more geologically violent world throughout its history, with its surface constantly recycling through active plate tectonics, volcanic eruptions, and erosion processes that destroy and remake the crust countless times, systematically erasing most direct evidence of its own turbulent youth. As both worlds spin through their first million years of existence, they accumulate the basic chemical ingredients for everything that will follow in their respective histories: water molecules delivered by cometary impacts, carbon compounds, and the fundamental chemistry necessary for geological and potentially biological change. The same population of comets that delivers vast quantities of water to Earth's gradually forming ocean basins also crashes repeatedly into Mars' heavily cratered highlands, depositing similar materials under similar conditions. Both planets receive essentially identical cosmic gifts from the outer solar system, yet they will unwrap and utilize these materials in entirely different ways over geological time. The gravitational signatures of both worlds during this period show similar patterns of mass distribution and rotational dynamics. Their surface temperatures, while extremely hot due to ongoing bombardment and radioactive decay, fall within comparable ranges. The chemical composition of their early atmospheres, dominated by carbon dioxide, water vapor, and trace gases released by volcanic outgassing, shows remarkable similarities when analyzed through spectroscopic studies of ancient mineral inclusions. Even their day lengths and seasonal cycles begin with comparable characteristics, before tidal forces and atmospheric evolution gradually modify their rotational behavior. In this primordial darkness, with both worlds still glowing cherry red from the residual heat of their violent formation process, the future remains entirely unwritten and unpredictable. The evolutionary pathways that will eventually lead one planet toward blue oceans teeming with microscopic life and green continents covered in complex ecosystems, while directing the other toward rust-colored deserts punctuated by polar ice caps and ancient riverbeds, have not yet begun to meaningfully diverge. For now, in this moment, suspended in deep time, Mars and Earth exist simply as two slowly cooling spheres of differentiated rock, sharing the same stellar neighborhood, breathing the same thin atmosphere of cosmic dust and solar radiation. The story of why Mars's carefully collected sample rocks matter so profoundly for understanding Earth's own history begins here. In this fleeting moment of planetary equality and similarity, two worlds with virtually identical cosmic pedigrees and chemical compositions, about to embark on separate evolutionary journeys that will reveal the profound contingency, delicate balance, and surprising unpredictability of planetary evolution itself across the vast scales of geological time. The Great Divergence begins not with catastrophe, but with mathematics, the simple equation of mass and gravity that will govern everything that follows. Mars, spinning in its orbit with only 38% of Earth's gravitational pull, cannot hold on to its gifts as tightly as its larger sibling. The same physics that allows a person to jump 3 times higher on Mars also allows atmospheric molecules to escape more easily into the vacuum of space. This fundamental relationship between planetary size and atmospheric retention will play out over hundreds of millions of years, so gradually that no single generation of hypothetical observers could perceive the change. Both worlds begin with substantial atmospheres, thick blankets of carbon dioxide and water vapor that trap heat from the young sun and create greenhouse conditions. The early Martian atmosphere may have been even denser than Earth's, fed by intense volcanic outgassing from the planet's molten interior. Olympus Mons and the other massive shield volcanoes of the Tharsis region begin their slow construction during this period, each eruption adding carbon dioxide, sulfur compounds, and water vapor to the thickening atmospheric envelope. The irony of this early abundance will not become apparent for another billion years. Mars starts its atmospheric life as the more volcanically active planet, pumping greenhouse gases into its sky with greater intensity than Earth. The magnetic field provides the invisible architecture that shapes atmospheric evolution. Deep within both planets, convecting liquid iron generates magnetic dynamos Earth's destined to persist for billions of years, Mars fated to weaken and eventually collapse. The difference lies in the delicate balance between core size, cooling rate, and the complex fluid dynamics of molten metal under pressure. Earth's larger mass allows its core to remain liquid longer, maintaining the convective motion necessary to generate magnetic field lines that extend far into space, creating a protective magnetosphere around the planet. Mars's magnetic field begins with similar strength, wrapping the planet in invisible lines of force that deflect the solar wind and protect the atmosphere from erosion. Ancient mineral deposits preserve the magnetic orientation of rocks formed during this period, creating a geological record of Mars's magnetic past. These paleomagnetic signatures, frozen into iron-bearing minerals as they cooled below their Curie temperature, serve as tiny compasses pointing toward a time when Mars possessed a global magnetic field comparable to Earth's modern magnetosphere. The mystery embedded in these rocks is poignant. They remember protection that no longer exists. As Mars's core begins to solidify, the convective motion that drives the magnetic dynamo gradually slows and eventually stops. The timing of this transition, occurring roughly 3.8 to 4.1 billion years ago, coincides with the end of the late heavy bombardment and the beginning of a more stable period in solar system evolution. Without the protective magnetic umbrella, Mars's atmosphere becomes vulnerable to a slow but relentless form of erosion, the solar wind. A stream of charged particles flowing constantly from the sun begins to strip away atmospheric molecules one by one. The process unfolds with geological patience. Solar wind particles, deflected around Earth by its magnetic field, strike Mars' unprotected atmosphere directly. They transfer energy to atmospheric molecules, accelerating them beyond the planet's escape velocity and carrying them away into interplanetary space. Lighter molecules, hydrogen from water vapor, carbon from carbon dioxide, prove most vulnerable to this atmospheric sputtering. Over millions of years, Mars begins to lose its ability to retain the greenhouse gases necessary to maintain warm surface temperatures. Earth's magnetic field, meanwhile, continues to strengthen and stabilize. The planet's larger core maintains sufficient heat and convective motion to power its magnetic dynamo for billions of years into the future. This invisible shield deflects most solar wind particles around the planet, creating the characteristic teardrop-shaped magnetosphere that extends far beyond Earth's atmosphere. The few charged particles that do penetrate this magnetic barrier create the aurora borealis and aurora australis, beautiful light displays that represent the successful operation of planetary magnetic protection. The atmospheric divergence accelerates as surface conditions on both planets begin to respond to their changing atmospheric compositions. Mars, losing its greenhouse gases to space, experiences gradual cooling that reduces the rate of water evaporation and volcanic outgassing. This creates a feedback loop as the atmosphere thins. Surface pressure drops, making liquid water less stable and further reducing atmospheric water vapor. Earth, retaining its atmospheric envelope, maintains warmer surface conditions that support active water cycles and continued volcanic outgassing, thickening rather than thinning its atmospheric blanket. Seasonal variations begin to play different roles on the two worlds. Earth's axial tilt of 23.5 degrees stabilized by the gravitational influence of its large moon, creates predictable seasonal cycles that help drive atmospheric circulation patterns. Mars' axial tilt, more variable due to the lack of a large stabilizing moon, experiences chaotic changes over geological timescales. These obliquity variations cause dramatic climate shifts, alternately burying and exposing polar ice caps, creating dust storms that can engulf the entire planet for months at a time. The volcanic activity that feeds both atmospheres begins to follow different patterns. Earth's plate tectonics, enabled by its larger size and higher internal heat production, creates a continuous cycle of crustal recycling that maintains volcanic activity over geological time. New oceanic crust forms at mid-ocean ridges, while old crust subducts at convergent margins, carrying water and carbon dioxide back into the mantle where they can be recycled through volcanic eruptions. Mars, too small to maintain active plate tectonics, relies on hotspot volcanism that gradually decreases as the planet's interior cools. The most profound irony of this early divergence lies in its invisibility to any hypothetical observers. The changes occur so gradually that they would remain imperceptible across thousands of lifetimes. Atmospheric pressure drops by fractions of a percent per million years. Magnetic field strength declines over periods longer than the evolution of complex life. Surface temperatures cool by degrees over epochs that dwarf human civilization. Yet, these minute changes, accumulated across geological time, transform worlds. Both planets continue to receive the same solar energy, orbit within the same stellar neighborhood, and experience similar cosmic influences. The fundamental difference lies in their capacity to hold on to the materials necessary for maintaining warm, wet surface conditions. Mars begins its transformation from a world of rivers and lakes toward a cold desert planet, while Earth's stronger gravity and persistent magnetic field allow it to retain the atmospheric thickness necessary for stable liquid water. The mathematical precision of planetary physics governs this great divergence, determining which world will preserve conditions suitable for life and which will gradually freeze into elegant sterility. Water's fleeting dance on Mars begins with the same cosmic choreography that fills Earth's first ocean basins. During the planet's youth, when its atmosphere still wraps thick and warm around the russet landscape, liquid water flows across the Martian surface with casual abundance. Rivers carve their signatures into ancient highlands, while lakes spread across impact basins, reflecting a pale sun through skies heavy with carbon dioxide and water vapor. The chemistry of this early hydrological cycle mirrors Earth's own awakening waters: evaporation, condensation, precipitation, and flow operating under the same fundamental physics that governs all planetary water systems. The evidence for this ancient aquatic Mars lies written in stone across the planet's surface. Valley networks, preserved in exquisite detail by the planet's geological stillness, trace the paths of rivers that meandered through landscapes 3.8 billion years ago. These channels, carved by flowing water over thousands of years, display the characteristic branching patterns of terrestrial river systems, tributaries joining main channels, meanders carved by persistent flow, deltas where rivers emptied into standing bodies of water. The preservation is so precise that planetary geologists can calculate flow rates, estimate seasonal variations, and reconstruct the hydrology of rivers that dried up before complex life appeared on Earth. Jezero Crater, where NASA's Perseverance rover now methodically collects samples, preserves one of Mars's most pristine ancient lake systems. The crater's rim, 45 kilometers across, once contained a body of water fed by at least 2 major river channels whose deltas still protrude into the crater floor like fossilized river mouths. Sedimentary layers within these deltas record the chemistry and temperature of Martian water during an epoch when both planets enjoyed warm, wet surface conditions. Each microscopic grain tells a story of erosion, transport, and deposition that parallels the sedimentary processes still active in Earth's river systems. The mystery embedded in these ancient waterways lies not in their existence, but in their brevity. Mars's rivers flowed for perhaps 200 million years, a substantial period by human standards, yet merely a geological moment compared to Earth's continuous water cycle spanning 4 billion years. The Martian hydrological system operated long enough to carve spectacular canyons, deposit vast sedimentary formations, and potentially support the chemical conditions necessary for life, yet brief enough that its traces remain largely unaltered by subsequent geological activity. Clay minerals scattered across Mars's ancient terrains preserve chemical signatures of this lost aquatic world. These hydrated silicates form only in the presence of liquid water under specific temperature and pH conditions, creating a mineral record of ancient Martian surface chemistry. Montmorillonite, nontronite, and saponite clay minerals identical to those forming in Earth's contemporary river deltas and lake beds document water-rock interactions that occurred when Mars still possessed a substantial atmosphere. The irony written in these clay deposits is profound. Mars preserves a more complete record of early aquatic conditions than Earth, whose active geology has recycled most evidence of its own primordial water systems. Orbital surveys reveal the full scope of Mars' ancient hydrological network. Thousands of valley systems thread across the planet's southern highlands, creating a drainage pattern that once rivaled Earth's major river basins in complexity and scale. The largest of these systems, carved by rivers that may have flowed continuously for millions of years, created channels hundreds of kilometers long and several kilometers wide. Some paleorivers carved their beds through solid bedrock, indicating persistent flow over geological timescales, while others show evidence of catastrophic flooding events that reshaped entire landscapes in geological instants. The chemical composition of Martian meteorites provides additional evidence for the planet's aquatic past. These rocks, blasted from Mars's surface by asteroid impacts and eventually captured by Earth's gravity after millions of years drifting through interplanetary space, contain mineral assemblages that could only have formed in the presence of liquid water. Carbonate deposits within these meteorites indicate that Mars once possessed surface waters with neutral to alkaline chemistry conditions similar to Earth's early oceans and potentially suitable for supporting primitive life forms. Seasonal water cycles operated on early Mars with surprising similarity to Earth's contemporary hydrological patterns. Computer models based on atmospheric pressure and temperature reconstructions suggest that Martian rivers experienced seasonal flooding and dry periods, creating patterns of erosion and deposition that mirror temperate terrestrial watersheds. Snow and ice accumulated in polar regions during Martian winters, then melted during spring and summer to feed river systems that transported sediments toward lower elevations and eventually into crater lakes and possible northern ocean basins. The transition from flowing rivers to frozen ground occurred gradually over tens of millions of years as Mars's atmosphere thinned and surface pressures dropped below the triple point of water. This critical threshold, 611 pascals pressure, at 0.01 degrees Celsius, represents the minimum conditions necessary for liquid water to exist on a planetary surface. As atmospheric pressure fell below this limit, Martian surface water could exist only as vapor or ice, ending the planet's era of rivers and lakes with thermodynamic finality. Subsurface water persisted long after surface rivers ceased to flow. Groundwater systems, protected from atmospheric loss by overlying rock layers, continued to circulate through Martian aquifers for hundreds of millions of years after surface water disappeared. Evidence for this subsurface hydrological activity appears in the form of minerals that precipitated from groundwater, creating veins and concretions that document the slow retreat of Mars's hidden water reserves deep underground. The timing of Mars's hydrological decline coincides precisely with the period when Earth's own water systems were achieving stability and abundance. While Martian rivers ran dry approximately 3.5 billion years ago, Earth's oceans were deepening and expanding, creating the vast aquatic environment that would eventually support the evolution of complex life. This temporal synchronization suggests that both planets experienced similar early conditions, but only Earth possessed the mass and magnetic protection necessary to maintain surface water over geological time. Modern Mars retains substantial water reserves in the form of polar ice caps and subsurface permafrost. Radar surveys indicate that frozen water underlies much of the planet's surface, particularly in polar and mid-latitude regions where seasonal temperature variations create freeze-thaw cycles. This hidden hydrosphere represents the remnant of Mars' once abundant surface water, now locked in solid form beneath a cold, thin atmosphere that can no longer support the liquid state on the surface. The samples being collected by Perseverance in Jezero Crater's ancient delta contain direct chemical evidence of Mars's lost rivers and lakes. Each grain of sediment carries isotopic signatures that record the temperature, chemistry, and seasonal variations of Martian water systems billions of years ago. When these samples eventually return to Earth, laboratory analysis will reveal precise details about Mars's hydrological cycle during the epoch when both planets possessed flowing surface water, creating a comparative study of planetary water systems separated by space but united by shared aquatic histories. Reading stones across time requires no human language, only the patient vocabulary of isotopes and crystal lattices that speaks the same truth whether examined on Earth or Mars. The Martian meteorites that have fallen to Earth over the past several thousand years carry encrypted messages about planetary formation, atmospheric evolution, and the deep chemistry of worlds. These fragments of alien geology, ejected from Mars by massive asteroid impacts and delivered to Earth after million-year journeys through interplanetary space, serve as natural samples from a world that humans have only recently begun to visit with robotic emissaries. Each meteorite tells multiple stories simultaneously. The mineral composition reveals the temperature and pressure conditions under which the rock originally formed in Mars's crust or mantle. The isotopic ratios of oxygen, carbon, and sulfur preserve chemical signatures of the Martian atmosphere during the epoch when the rock crystallized. Microscopic inclusions of ancient Martian atmosphere, trapped within crystal defects and mineral boundaries, provide direct samples of gases that surrounded Mars billions of years ago. The cosmic ray exposure ages, measured through the accumulation of rare isotopes produced by high-energy radiation during the meteorite's journey through space, document precisely how long each fragment drifted between the planets. The most famous of these stone messengers, designated ALH8431, preserves a record of Mars's ancient subsurface environment in extraordinary detail. This 4.1 billion-year-old fragment of Martian crust contains carbonate minerals that precipitated from groundwater systems operating deep beneath the planet's surface during the Noachian epoch. The chemical composition of these carbonates indicates that subsurface Martian water possessed neutral pH and moderate temperatures conditions remarkably similar to those found in Earth's deep groundwater systems today. The irony embedded in this ancient rock is striking. A piece of Mars discovered in Antarctica reveals more about early Martian water chemistry than decades of orbital observations. Shergottites, the most abundant class of Martian meteorites, originated from volcanic regions of Mars and preserve isotopic evidence of the planet's atmospheric evolution over geological time. The ratio of argon isotopes trapped within these rocks documents the gradual loss of Mars' atmosphere to space, providing quantitative measurements of atmospheric escape rates spanning hundreds of millions of years. Each crystal acts as a microscopic barometer, recording atmospheric pressure at the time of volcanic crystallization and creating a timeline of Mars' atmospheric decline that can be read with isotopic precision. The Naklites, another family of Martian meteorites, formed in volcanic environments where magma interacted extensively with subsurface water. These rocks contain hydrated minerals that crystallize directly from aqueous solutions, preserving chemical fingerprints of water-rock interactions that occurred approximately 1.3 billion years ago. The trace element compositions of these hydrated phases reveal that Martian groundwater systems remained active long after surface rivers had dried up, maintaining subsurface habitable environments for hundreds of millions of years after Mars's surface became uninhabitable. Chassignites, the rarest Martian meteorites, originated from the planet's mantle and provide unique insights into Mars's deep interior chemistry. These ultramafic rocks contain mineral assemblages that formed under high pressure and temperature conditions deep within the planet, yet they also show evidence of interaction with aqueous fluids during their journey toward the surface. The presence of both high-temperature mantle minerals and low-temperature alteration products within the same rock sample documents the complex pathways through which Martian magmas interacted with groundwater during volcanic eruptions. Cosmic ray exposure dating reveals the violence required to launch these rocks from Mars toward Earth. The impact energies necessary to accelerate rocks beyond Mars' escape velocity, approximately 5 kilometers per second, indicate asteroid collisions powerful enough to create craters tens of kilometers in diameter. These catastrophic events, occurring perhaps once every million years, excavate rocks from depths of several kilometers beneath Mars's surface and scatter them across the solar system like geological shrapnel. The fact that Earth has received dozens of these samples represents an extraordinary statistical coincidence, fragments of another world delivered naturally to terrestrial laboratories. The isotopic composition of water trapped within Martian meteorites provides direct evidence for the planet's atmospheric history. The ratio of deuterium to hydrogen in these ancient water samples is significantly higher than the ratio found in Earth's oceans, indicating that Mars has lost most of its original water inventory to space through atmospheric escape. Light hydrogen atoms escape more easily than heavy deuterium atoms, gradually enriching the remaining water in the heavier isotope. This isotopic fractionation serves as a quantitative measure of how much water Mars has lost over geological time. Organic compounds preserved within some Martian meteorites add another layer of complexity to the story these stones tell. Simple carbon molecules, including polycyclic aromatic hydrocarbons and aliphatic chains, appear in mineral veins and crystal boundaries where they have remained stable for billions of years. The origin of these organic compounds remains mysterious. They could represent the products of prebiotic chemistry, biological activity, or purely geological processes involving carbon-bearing fluids. Their mere presence demonstrates that Mars possessed the chemical ingredients necessary for complex carbon chemistry during its early history. The magnetic properties of Martian meteorites preserve evidence of the planet's ancient magnetic field. Microscopic magnetic minerals within these rocks retain weak magnetization aligned with magnetic field directions that existed when the rocks cooled below their Curie temperature. This paleomagnetic evidence confirms that Mars once possessed a global magnetic field similar in strength to Earth's current magnetic field, providing crucial data about the timing and intensity of Mars's magnetic dynamo before it permanently shut down. Laboratory analysis of Martian meteorites requires extraordinary contamination control to distinguish truly Martian signatures from terrestrial contamination acquired during the rock's residence on Earth. Each sample undergoes careful cleaning and preparation in sterile environments, followed by analysis using the most sensitive analytical techniques available to terrestrial science. Mass spectrometry, electron microscopy, and X-ray crystallography reveal isotopic ratios, mineral compositions, and crystal structures with precision measured in parts per million or better. The mystery that emerges from reading these stones lies in the fundamental similarity between Martian and terrestrial geological processes. Despite forming on different worlds under different conditions, Martian rocks show evidence for igneous differentiation, aqueous alteration, and metamorphic processes that closely parallel those operating on Earth. This convergent geology suggests that the basic physics and chemistry of planetary evolution follow similar pathways regardless of planetary size or distance from the Sun, creating recognizable patterns that can be decoded by terrestrial scientists working in laboratories millions of kilometers from the rock's origins. Future sample return missions will exponentially expand this natural meteorite collection, providing carefully selected specimens from known geological contexts rather than random fragments delivered by chance impacts. The combination of Martian meteorites and sample return specimens will create an unprecedented library of comparative planetary geology, allowing scientists to read the deep history of two worlds through the patient language of stones that remember everything and forget nothing across billions of years of cosmic time. The magnetic shield's collapse unfolds with the inevitability of planetary physics, yet its consequences ripple across geological time with profound subtlety. Deep within Mars' cooling interior, the convective motion of liquid iron that has generated the planet's protective magnetic field for hundreds of millions of years begins to slow as thermal gradients decrease and the core gradually solidifies. This transition occurs not as sudden catastrophe, but as gradual weakening magnetic field strength declining by imperceptible fractions over millions of years until the dynamo finally stills completely, leaving Mars exposed to the solar wind's relentless erosion. The timing of this magnetic collapse, approximately 4.1 billion years ago, coincides with a critical period in solar system evolution when the young sun was beginning to settle into its stable main sequence burning phase. During this epoch, solar radiation intensity fluctuated more dramatically than in the modern era, creating periods of enhanced solar wind activity that stripped atmospheric particles from unprotected planetary surfaces with increased efficiency. Mars loses its magnetic protection precisely when that protection becomes most crucial for atmospheric retention, creating a cosmic coincidence of unfortunate timing that will determine the planet's evolutionary trajectory for the next 4 billion years. Evidence for Mars's lost magnetic field lies scattered across the planet's ancient terrain in the form of magnetized crustal rocks that preserve fossil records of the dynamo's final centuries. These paleomagnetic signatures, frozen into iron-bearing minerals as they cooled below their Curie temperature while Mars still possessed a global magnetic field, create a geological map of magnetic field directions and intensities during the planet's magnetic epoch. The strongest crustal magnetization occurs in the southern highlands, where rocks older than 4 billion years retain magnetic field strengths comparable to those found near Earth's most intensely magnetized geological formations. The pattern of crustal magnetization reveals the structure and behavior of Mars's ancient magnetic field with remarkable precision. Linear magnetic anomalies, stretching for hundreds of kilometers across the planet's southern hemisphere, suggest that Mars may have experienced a brief period of plate tectonics during which new crust formed at spreading centers and acquired magnetic orientation from the global dynamo. These magnetic stripes, similar to those found on Earth's ocean floors, provide evidence that Mars once possessed geological processes more similar to Earth's than previously recognized, including the possibility of continental drift and seafloor spreading. Earth's magnetic field, meanwhile, continues to strengthen and stabilize as the planet's larger mass maintains sufficient internal heat to drive vigorous convection within its liquid outer core. The terrestrial magnetic dynamo operates through the complex interaction of thermal convection, planetary rotation, and electrical conductivity within the molten iron-nickel alloy that surrounds Earth's solid inner core. This self-sustaining electromagnetic system generates magnetic field lines that extend tens of thousands of kilometers into space, creating the magnetosphere that deflects most solar wind particles around the planet and maintains a protective barrier against cosmic radiation. The loss of magnetic protection exposes Mars's atmosphere to a form of erosion that operates continuously but imperceptibly across geological timescales. Solar wind particles, traveling at speeds of 300 to 800 kilometers per second, strike unprotected atmospheric molecules and transfer sufficient kinetic energy to accelerate them beyond Mars' escape velocity. This process, known as atmospheric sputtering, preferentially removes lighter atmospheric constituents hydrogen from water vapor, carbon from carbon dioxide, nitrogen from trace atmospheric gases, gradually altering the chemical composition of the remaining atmosphere while reducing its total mass and pressure. The rate of atmospheric loss accelerates during periods of intense solar activity when coronal mass ejections and solar flares increase the density and energy of the solar wind. Modern spacecraft orbiting Mars have measured atmospheric escape rates during these events and found that Mars can lose as much atmosphere in a single day of intense solar activity as it typically loses over several months of quiet solar conditions. Extrapolating these measurements backward across geological time suggests that Mars has lost the equivalent of several Earth atmospheres to space since the collapse of its magnetic field, transforming a once thick atmospheric envelope into the thin carbon dioxide atmosphere that exists today. The chemical signatures of this atmospheric escape remain preserved in the isotopic composition of Mars' current atmosphere and surface materials. The ratio of argon-38 to argon-36 in the Martian atmosphere shows clear evidence of preferential loss of the lighter isotope, while the deuterium to hydrogen ratio in water ice and hydrated minerals indicates that Mars has lost approximately 85% of its original water inventory to space. These isotopic fingerprints provide quantitative measurements of atmospheric evolution that can be compared directly with Earth's atmospheric composition to understand how magnetic protection influences planetary habitability over geological time. Earth's magnetosphere creates a complex interaction with the solar wind that generates beautiful consequences alongside its protective function. When solar wind particles do penetrate the magnetic field at polar regions, they collide with atmospheric gases and create the aurora borealis and aurora australis shimmering curtains of light that represent the successful operation of planetary magnetic defense. These auroral displays serve as visible evidence that Earth's magnetic field continues to deflect the vast majority of solar wind energy around the planet, maintaining atmospheric stability across geological timescales. The geometry of planetary magnetic fields determines their effectiveness at atmospheric protection. Earth's dipolar magnetic field, with clearly defined north and south magnetic poles, creates a streamlined magnetosphere that efficiently channels solar wind particles around the planet. Mars's ancient magnetic field may have possessed a more complex multipolar structure, based on the distribution of crustal magnetic anomalies, potentially making it less effective at deflecting solar wind even before the dynamo failed completely. This geometric difference suggests that magnetic field structure, not just strength, plays a crucial role in determining long-term atmospheric retention. Regional magnetic anomalies on Mars continue to provide localized atmospheric protection even after the global dynamo ceased operation. These crustal magnetic fields, remnants of the planet's magnetic past, create small-scale magnetospheres that deflect solar wind particles over areas hundreds of kilometers in diameter. Spacecraft measurements show that atmospheric loss rates vary significantly across Mars's surface, with regions of strong crustal magnetization experiencing lower escape rates than areas where crustal magnetic fields are weak or absent. This patchy protection creates a complex pattern of atmospheric erosion that continues to shape Mars's thin atmosphere today. The irony of magnetic protection lies in its invisibility during normal operation and its consequences during failure. Earth's magnetic field operates silently and continuously, deflecting potentially lethal cosmic radiation and maintaining atmospheric stability without any visible indication of its protective function except for the occasional aurora display. Mars's magnetic field operated with similar invisibility during the planet's youth, providing atmospheric protection that became apparent only through its absence. The loss of this invisible shield transformed Mars from a world capable of supporting liquid water and potentially life into a cold, dry planet where surface conditions gradually became hostile to biological activity. Modern Mars missions continue to study the planet's magnetic environment and its effects on atmospheric evolution. The MAVEN spacecraft measures current atmospheric escape rates and their relationship to solar activity, while rovers and landers analyze surface materials for evidence of past atmospheric conditions. These ongoing studies reveal that atmospheric loss continues today, albeit at much slower rates than during the period immediately following magnetic field collapse, as Mars's thin atmosphere has reached a quasi-equilibrium between ongoing loss and replenishment from volcanic outgassing and sublimation of polar ice deposits. Perseverance's quiet harvest unfolds with robotic patience across the ancient lakebed of Jezero Crater, where each carefully selected sample represents millions of years of Martian geological history compressed into fragments no larger than a human thumb. The rover moves with deliberate precision across terrain that once knew flowing water, its mechanical systems designed to operate flawlessly in the thin carbon dioxide atmosphere, while temperatures swing between -80 degrees Celsius during Martian nights and barely above freezing during the warmest summer afternoons. Every operation, from drilling core samples to sealing them within sterile titanium tubes, follows protocols developed over decades to ensure that these precious geological specimens remain uncontaminated during their eventual journey back to Earth. The drilling process itself requires extraordinary engineering precision adapted to Martian conditions. Perseverance's rotary percussive drill system must penetrate rocks that have been hardened by billions of years of exposure to cosmic radiation and extreme temperature cycling, while avoiding contamination from terrestrial materials or the rover's own mechanical systems. Each drilling operation consumes several hours as the drill slowly advances through centimeters of ancient Martian bedrock, generating rock powder and extracting intact core samples that preserve the original mineral textures and chemical compositions formed during Mars' ancient past. Sample selection follows careful geological logic designed to maximize scientific return from the limited number of samples that can eventually be transported back to Earth. The mission's science team analyzes high-resolution images and spectroscopic data from each potential sampling site, looking for rocks that formed under different environmental conditions and preserve evidence of various geological processes. Igneous rocks document the composition and temperature of ancient Martian magmas. Sedimentary rocks preserve evidence of water activity and surface environmental conditions, and altered rocks reveal the chemistry of subsurface fluids that interacted with the original minerals over geological time. The sample caching system represents one of the most sophisticated robotic operations ever attempted on another planet. After drilling and analyzing each core sample, Perseverance transfers the specimen to a hermetically sealed titanium tube approximately the size and shape of a large test tube. These sample containers undergo careful cleaning and sterilization procedures before sealing to prevent cross-contamination between samples and to eliminate any possibility of terrestrial biological contamination. The sealed tubes are then deposited at predetermined locations across Jezero Crater, creating a carefully mapped sample depot that future sample return missions can locate and retrieve with centimeter-level precision. Each sample tube contains not just rock fragments, but also a measured volume of Martian atmosphere captured at the moment of sealing. This atmospheric sample preserves the exact isotopic composition of modern Martian air, providing baseline measurements against which ancient atmospheric compositions preserved in the rock samples can be compared. The atmospheric samples also contain trace amounts of water vapor, methane, and other gases that vary seasonally and regionally across Mars, creating a comprehensive chemical snapshot of the planet's current atmospheric state for comparison with conditions that existed billions of years ago. The geological context of Jezero Crater makes it an ideal location for sampling ancient Martian environments. The crater formed approximately 9 billion years ago during the late heavy bombardment, when massive asteroid impacts carved basins across the surfaces of terrestrial planets throughout the inner solar system. Subsequently, Jezero became the site of a substantial lake system fed by rivers that carved channels through the crater rim and deposited sedimentary layers across the crater floor. These deposits preserve a detailed record of Martian surface conditions during the planet's most Earth-like epoch, when flowing water and potentially habitable environments existed across much of the planet's surface. The rover's analytical instruments provide preliminary characterization of each sample before it undergoes the complex catching process. X-ray fluorescence spectroscopy reveals the elemental composition of target rocks, while infrared spectroscopy identifies specific minerals and their hydration states. Ground-penetrating radar maps subsurface layering and structure, helping scientists understand the geological context in which each sample formed. High-resolution cameras document surface textures and geological relationships that preserve information about depositional environments and subsequent alteration processes. Ancient delta deposits within Jezero Crater receive special attention from the sampling strategy due to their exceptional potential for preserving evidence of past life. River deltas on Earth concentrate organic matter and create environments where biological materials can be rapidly buried and preserved over geological timescales. The Martian delta deposits contain fine-grained sedimentary layers that accumulated grain by grain as ancient rivers deposited their sediment loads into the crater lake, creating ideal conditions for preserving any organic compounds or biological signatures that might have existed in the Martian surface environment 3.5 billion years ago. The sampling operations must account for the complex contamination challenges inherent in interplanetary sample collection. Every component of the drilling and caching system undergoes extensive sterilization procedures before launch to eliminate terrestrial microorganisms that could potentially survive the journey to Mars and contaminate the samples. The rover carries witness plates, ultra-clean reference materials that travel through the same procedures as the rock samples, allowing scientists to detect and account for any contamination introduced during sample collection, storage, or transport back to Earth. Seasonal timing influences the sampling campaign, as Martian weather patterns affect both rover operations and sample preservation. Dust storms can reduce solar power generation and limit drilling operations, while temperature extremes affect the mechanical properties of both the sampling equipment and the target rocks. The mission timeline coordinates sampling activities with optimal environmental conditions, ensuring that each sample undergoes collection and sealing under the best possible circumstances for preserving its original chemical and isotopic compositions. The diversity of samples collected across Jezero Crater creates a comprehensive geological survey of ancient Martian environments. Igneous rocks from the crater floor preserve evidence of volcanic activity and crustal composition during Mars's early history. Sedimentary rocks from the delta deposits document surface water chemistry and depositional environments during the planet's most habitable epoch. Altered rocks showing evidence of groundwater interaction reveal the chemistry and temperature of subsurface fluids that circulated through Martian aquifers long after surface water disappeared. Each sample tube bears unique identification markers that will allow scientists to track individual specimens through the complex process of sample return, terrestrial quarantine, and laboratory analysis. These identifiers link each physical sample to its precise geological context, analytical measurements made on Mars, and high-resolution images documenting the sampling site. This comprehensive documentation ensures that the geological story preserved in each sample can be fully reconstructed and interpreted when the specimens eventually reach terrestrial laboratories equipped with analytical instruments far more sophisticated than those carried by robotic missions. The irony of this robotic harvest lies in its reversal of the natural meteorite delivery process that has provided Earth with Martian samples for millennia. Instead of waiting for random cosmic collisions to launch Martian rocks toward Earth, human technology now enables the deliberate selection and collection of samples from specific geological contexts that maximize scientific understanding of Martian history. This technological capability transforms the study of comparative planetology from a science dependent on fortunate accidents into a systematic investigation guided by scientific hypotheses and geological understanding. Modern sample collection represents only the first phase of a multi-mission campaign designed to return Martian rocks to Earth for comprehensive laboratory analysis. Future missions will retrieve the cached samples and launch them toward Earth in a sample return vehicle designed to preserve specimen integrity during the journey through interplanetary space. The successful completion of this sample return campaign will provide terrestrial laboratories with the first carefully selected and documented samples from another planet, revolutionizing understanding of planetary evolution and the potential for life beyond Earth. Olevine's whispered secrets lie locked within crystal lattices that formed in the heart of ancient Martian magma chambers, where temperatures exceeded 1200 degrees Celsius and pressures crushed rock into new molecular arrangements with mathematical precision. These green-tinted silicate minerals, composed of iron, magnesium, silicon, and oxygen arranged in ordered crystalline structures, preserve chemical fingerprints of the conditions under which they crystallized billions of years ago. Each olivine grain acts as a geological thermometer and barometer, recording the exact temperature, pressure, and chemical environment that existed when molten rock slowly cooled and solidified deep beneath Mars' ancient surface. The olivine crystals found in Martian meteorites and detected by rovers across the planet's surface reveal fundamental similarities between Martian and terrestrial magmatic processes. On both worlds, olivine forms as one of the first minerals to crystallize from cooling basaltic magma, settling out of the molten mixture when temperatures drop below approximately 1300 degrees Celsius. The chemical composition of olivine reflects the composition of the parent magma, with iron-rich olivines indicating magmas derived from iron-rich source rocks, while magnesium-rich olivines suggest magmas generated from more primitive mantle materials This direct relationship between olivine chemistry and magma composition allows scientists to reconstruct the thermal and chemical evolution of both planets' interiors. Spectroscopic analysis of olivine-rich regions on Mars reveals variations in mineral composition that document the planet's igneous diversity across different geographical regions and geological time periods. The Nili Fossae region, located on the rim of the massive Isidis Impact Basin, contains some of the most olivine-rich terrain on Mars, suggesting that the impact event excavated deep crustal or upper mantle rocks and exposed them at the surface. These ancient olivine-bearing rocks preserve chemical signatures of Martian magmatic processes that operated during the planet's earliest geological epoch, providing insights into the composition and thermal state of Mars' interior during the first billion years of its existence. The preservation of olivine on Mars's surface contrasts sharply with its rarity in Earth's surface rocks, revealing fundamental differences in the weathering environments of the two planets. Olivine weathers rapidly in the presence of liquid water and acidic conditions, transforming into clay minerals and iron oxides through chemical alteration processes that erase the original mineral's chemical signatures. The abundance of unaltered olivine across large areas of Mars indicates that liquid water was either absent or present only briefly in those regions, suggesting that much of Mars's surface has remained dry for billions of years since the olivine-bearing rocks were first exposed through impact cratering or volcanic activity. Microscopic analysis of olivine grains within Martian meteorites reveals complex zoning patterns that document the thermal history of individual magma chambers during cooling and crystallization. These zoning patterns, created by subtle changes in iron and magnesium content from the core to the rim of individual crystals, preserve a chronological record of how magma composition evolved during crystallization. Early formed crystal cores preserve the composition of primitive magma, while later formed rims document how the remaining liquid evolved as other minerals crystallized and removed specific elements from the magma. This mineral scale record provides insights into crystallization processes that operated within Martian magma chambers over thousands of years. The isotopic composition of oxygen within Martian olivine provides crucial evidence for the planet's formation history and early atmospheric evolution. Oxygen isotope ratios in planetary materials preserve signatures of the temperature and chemical conditions under which minerals formed, with different isotopic compositions indicating formation under different environmental conditions. Martian olivine shows oxygen isotope ratios that are distinctly different from terrestrial minerals, confirming that Mars formed from a different reservoir of materials within the early solar nebula. These isotopic differences provide quantitative constraints on models of planetary accretion and the distribution of materials within the forming solar system. The trace element chemistry of olivine crystals reveals information about the deep interior processes that generated Martian magmas. Elements like nickel, chromium, and calcium substitute for iron and magnesium in olivine crystal structures at levels determined by temperature, pressure, and the availability of these elements in the parent magma. The concentration of these trace elements in Martian olivine indicates that many Martian magmas were generated by partial melting of mantle rocks at depths of 50 to 150 kilometers beneath the planet's surface, under pressure and temperature conditions similar to those that generate basaltic magmas on Earth. Shock, metamorphic features within some Martian olivine grains document the violent impact events that excavated these minerals from deep within the planet and eventually launched them toward Earth as meteorites. High-pressure polymorphs of olivine, including ringwoodite and wadsleyite, form only under the extreme pressures generated during large asteroid impacts. The presence of these high-pressure minerals within Martian meteorites indicates that the impact events responsible for launching rocks from Mars toward Earth were catastrophic collisions that generated pressures exceeding 20 gigapascals, equivalent to the pressure found 600 kilometers beneath Earth's surface. The distribution of olivine across Mars's surface reveals patterns related to the planet's geological evolution and the timing of major impact events. Large impact basins like Hellas and Argyre are surrounded by rings of olivine-rich terrain where the impact excavated deep crustal rocks and exposed them at the surface. Volcanic regions like Syrtis Major and the Tharsis volcanic province show different olivine compositions related to the diverse magmas that erupted from Mars' interior over billions of years. These regional variations in olivine chemistry provide a geological map of Mars' igneous evolution that can be read through orbital spectroscopy and rover-based analysis. The crystallographic structure of olivine makes it particularly sensitive to temperature changes, allowing scientists to reconstruct the thermal history of Martian rocks with unprecedented precision. Olivine crystals undergo subtle structural changes when exposed to elevated temperatures during metamorphic heating events, creating features that can be detected through X-ray crystallography and electron microscopy. Analysis of olivine crystal structures in Martian meteorites reveals that most have experienced minimal thermal alteration since their formation, indicating that Mars's crust has remained relatively cool and geologically inactive compared to Earth's continuously recycling lithosphere. Laboratory experiments using synthetic olivine compositions identical to those found in Martian rocks allow scientists to calibrate the relationship between olivine chemistry and formation conditions with extraordinary precision. These experimental studies, conducted under controlled temperature and pressure conditions that simulate Martian magma chamber environments, provide quantitative relationships between mineral composition and crystallization conditions. The results enable scientists to convert mineral chemistry measurements into precise estimates of temperature, pressure, and magma composition for ancient Martian volcanic systems. The mystery embedded within Martian olivine lies in its chemical diversity, which exceeds that found in many terrestrial volcanic systems, despite Mars's smaller size and presumably simpler geological evolution. This diversity suggests that Mars's mantle possesses complex chemical heterogeneity that developed during the planet's early differentiation or was inherited from the original accretionary materials. The preservation of this chemical complexity over billions of years indicates that Mars' interior has remained relatively unmixed compared to Earth's mantle, which undergoes continuous convective stirring that homogenizes chemical variations over geological time. Future laboratory analysis of olivine-bearing samples returned from Mars will provide unprecedented insights into the planet's magmatic evolution and interior chemistry. Terrestrial analytical instruments can measure isotopic compositions, trace element concentrations, and crystallographic structures with precision far exceeding that possible with robotic missions. These detailed measurements will reveal the thermal and chemical conditions under which Martian magmas formed, crystallized, and evolved, creating a comprehensive understanding of how Mars' interior has operated over the past 4.5 billion years, and how it compares to the magmatic processes that continue to shape Earth's geology today. The clay chronicles unfold across Mars' ancient landscapes in microscopic mineral libraries that preserve the most intimate details of water-rock interactions from an epoch when the planet's surface knew gentle chemistry and patient hydration. These phyllosilicate minerals, formed through the slow transformation of volcanic glass and primary silicate minerals in the presence of liquid water, document precise pH conditions, temperature ranges, and chemical compositions of ancient Martian surface waters with forensic accuracy. Each clay crystal represents thousands of years of molecular-scale chemical reactions between flowing water and basaltic bedrock, creating mineral assemblages that serve as geological pH meters and thermometers for environments that existed billions of years before Earth developed complex life. Montmorillonite, the most abundant clay mineral detected across Mars' ancient terrains, forms under neutral to slightly alkaline water conditions at temperatures between 0 and 25 degrees Celsius, precisely the range that characterizes temperate terrestrial environments today. The crystal structure of Montmorillonite incorporates water molecules between its silicate layers, creating a swelling clay that preserves not only the chemical signature of the water from which it formed, but also organic molecules and trace elements that were dissolved in those ancient Martian solutions. The irony written in these humble minerals is profound. Mars preserves a more complete record of early aqueous geochemistry than Earth, whose active water cycle continuously dissolves and recrystallizes clay minerals, erasing their original chemical signatures. Orbital surveys reveal extensive clay-bearing terrains concentrated in Mars' ancient highlands, particularly in regions like Mawth Vallis, Neely Fosse, and the rim materials surrounding large impact basins. These clay deposits form stratigraphic layers hundreds of meters thick, indicating that clay-forming conditions persisted across substantial geographical areas for millions of years during Mars's early history. The thickness and lateral extent of these deposits suggest that water-rock interaction operated as a global process rather than isolated local phenomena, documenting planet-wide aqueous activity during the transition from Mars' volcanic youth to its current arid state. The chemical diversity of Martian clay minerals reveals the range of geochemical environments that existed during the planet's aqueous epoch. Nontronite, an iron-rich clay mineral, forms under moderately acidic conditions where iron-bearing volcanic rocks undergo chemical weathering in the presence of flowing water. Saponite, a magnesium-rich phyllosilicate, indicates interaction between water and ultramafic rocks under neutral to alkaline pH conditions. Kaolinite, an aluminum-rich clay, forms through intensive chemical weathering that leaches mobile elements like sodium, potassium, and calcium from volcanic rocks, while concentrating aluminum and silicon in stable mineral structures. Spectroscopic analysis of clay-bearing outcrops reveals systematic variations in mineral composition that document changing environmental conditions during Mars' aqueous history. Lower stratigraphic layers often contain iron and magnesium-rich clays formed during early, neutral pH conditions, while upper layers show aluminum-rich clays that formed under increasingly acidic conditions as Mars' climate evolved. This stratigraphic progression records a systematic change in surface water chemistry from benign, potentially habitable conditions toward more acidic environments that would have been challenging for any hypothetical biological systems. The preservation state of Martian clay minerals provides crucial information about subsequent environmental conditions since their formation. Unlike olivine, which weathers rapidly in aqueous environments, clay minerals represent the stable end products of chemical weathering processes and can persist for billions of years under arid conditions. The excellent preservation of clay mineral crystal structures across Mars's surface indicates that most clay-bearing terrains have remained dry since their formation, suggesting that the planet's major aqueous epoch was relatively brief in geological terms, lasting perhaps only a few 100 million years during the late Noachian and early Hesperian periods. Laboratory analysis of clay-bearing Martian meteorites reveals trace element compositions that document the chemistry of ancient Martian surface waters with extraordinary precision. Elements like boron, lithium, and beryllium, which are highly mobile in aqueous solutions, become incorporated into clay mineral structures during formation and preserve records of the trace element chemistry of the waters from which they crystallized. These geochemical signatures indicate that ancient Martian surface waters contained dissolved salts and trace metals at concentrations similar to those found in terrestrial groundwater systems, suggesting broadly similar geochemical processes despite the different planetary environments. The discovery of hydrated sulfate minerals interlayered with clay deposits reveals the complex chemical evolution of Martian surface waters over geological time. Gypsum, jarosite, and other sulfate minerals form under more acidic conditions than most clay minerals, indicating that water chemistry evolved from neutral alkaline toward acidic compositions during Mars's aqueous history. This chemical evolution may reflect changes in volcanic gas compositions, atmospheric chemistry, or the progressive concentration of dissolved salts as surface water became scarce and evaporation rates increased. Microscopic analysis of clay minerals within sedimentary rocks collected by Mars rovers reveals textural relationships that document depositional environments and post-depositional alteration processes. Clay minerals that formed through in situ chemical weathering show different crystal sizes and morphologies than clays that formed elsewhere and were subsequently transported and deposited by flowing water. These textural differences allow scientists to distinguish between clays formed through local water-rock interaction and those that represent sedimentary deposits transported from distant weathering environments. The isotopic composition of hydrogen and oxygen within hydrated Martian clay minerals preserves isotopic signatures of ancient Martian water that can be compared directly with the isotopic composition of water in Mars' current atmosphere and polar ice caps. The deuterium to hydrogen ratios in clay-bound water are significantly lower than ratios in modern Martian water, indicating that the clay minerals formed from ancient water that had undergone less atmospheric escape and isotopic fractionation. This isotopic evidence provides quantitative constraints on the amount of water Mars has lost to space since the clay-forming epoch. The distribution of clay minerals across Mars's surface correlates strongly with age relationships determined through crater counting and stratigraphic analysis. The oldest terrains, dating to the early Noachian period, more than 4 billion years ago, show the most extensive clay mineral deposits, while younger surfaces show progressively less evidence for aqueous alteration. This temporal relationship documents the decline of aqueous activity on Mars over geological time, with major clay formation ending approximately 3.5 billion years ago as the planet's climate transitioned toward its current arid state. Experimental studies using Martian analog minerals demonstrate the specific conditions required for clay mineral formation under Martian environmental constraints. Laboratory experiments that expose basaltic compositions to water under low pressure, low temperature conditions that simulate early Martian surface environments, successfully reproduce the mineral assemblages observed in Martian clay deposits. These experiments reveal that clay formation requires sustained water-rock interaction over timescales of thousands to millions of years, indicating that Mars maintained stable hydrological systems for geologically significant periods during its early history. The mystery embedded within Martian clay deposits lies in their abrupt termination rather than their formation. While the conditions required for clay mineral formation are well understood and easily reproduced in laboratory settings, the rapid cessation of clay-forming processes across Mars remains enigmatic. The transition from widespread aqueous alteration to arid surface conditions appears to have occurred within a relatively brief geological interval, suggesting that Mars's climate system underwent rapid and irreversible change approximately 3.5 billion years ago. Future sample return missions will provide unprecedented opportunities to analyze Martian clay minerals using sophisticated terrestrial analytical techniques that can reveal isotopic compositions, trace element distributions, and structural details at the atomic scale. These analyses will decode the complete geochemical story preserved within clay mineral structures, revealing precise temperatures, pH values, and chemical compositions of ancient Martian waters. The clay chronicles will thus provide a detailed reconstruction of Mars's aqueous environments during the epoch when the planet most closely resembled Earth's current habitable conditions. Organic molecules in stone whisper the most tantalizing secrets across the vast silence of geological time. Their carbon-based structures, preserved within Martian rocks like molecular fossils that remember the chemistry of ancient worlds. These complex arrangements of carbon, hydrogen, oxygen, and nitrogen atoms, detected within meteorites from Mars and measured by robotic laboratories crawling across the planet's surface, represent either the chemical signatures of extinct biological processes or the products of purely geological carbon chemistry operating under conditions that mirror those found in Earth's most primitive environments. The distinction between biological and abiological organic compounds remains one of the most profound mysteries in planetary science, with implications that extend far beyond the boundaries of individual worlds. The discovery of organic molecules within the 4.1 billion-year-old Martian meteorite ALH8 4001 created scientific controversy that continues to shape astrobiology research decades later. Polycyclic aromatic hydrocarbons, amino acid precursors, and other carbon-rich compounds appear concentrated within carbonate globules that formed during low-temperature aqueous alteration of the meteorite's original igneous minerals. These organic molecules show isotopic compositions that differ subtly from known terrestrial contamination, suggesting they originated on Mars rather than being introduced during the meteorite's residence on Earth. Yet their concentrations remain frustratingly low, requiring the most sensitive analytical techniques available to terrestrial science to detect and characterize their molecular structures. Curiosity's analysis of organic compounds within sedimentary rocks in Jezero Crater reveals a more diverse suite of carbon-based molecules than previously detected in any extraterrestrial materials. Thiophene, benzene, toluene, and other aromatic compounds emerge from Martian mudstones when heated to temperatures exceeding 500 degrees Celsius, suggesting that larger organic macromolecules decompose during analysis to produce these smaller molecular fragments. The presence of sulfur-bearing organic compounds indicates that ancient Martian organic chemistry involved complex interactions between carbon, sulfur, and other elements under reducing conditions that favor organic molecule preservation over geological timescales. The concentration and distribution of organic molecules within Martian rocks show systematic patterns that provide clues about their origin and preservation mechanisms. Organic compounds appear most abundant in fine-grained sedimentary rocks deposited in lacustrine environments, where rapid burial and anoxic conditions would favor organic matter preservation. Coarser-grained rocks and those showing evidence of extensive oxidation contain lower organic concentrations, suggesting that exposure to oxidizing conditions destroys organic molecules over geological time. This preservation pattern mirrors organic matter distribution in terrestrial sedimentary rocks, where fine-grained marine and lacustrine deposits preserve the highest concentrations of ancient biological materials. The molecular structures of Martian organic compounds reveal both similarities and differences compared to organic molecules found in carbonaceous meteorites and terrestrial geological systems. Simple aliphatic hydrocarbons, consisting of carbon and hydrogen atoms arranged in straight and branched chains, appear in both Martian rocks and carbonaceous chondrites, suggesting common formation mechanisms that operate throughout the solar system. More complex aromatic compounds, featuring ring structures of carbon atoms, show structural characteristics that could indicate either biological processes or high-temperature geochemical synthesis during hydrothermal circulation or impact metamorphism. Isotopic analysis of carbon within Martian organic molecules provides crucial information about their formation mechanisms and potential biological significance. Biological processes preferentially incorporate the lighter carbon-12 isotope relative to carbon-13, creating isotopic signatures that can distinguish biological from abiological carbon compounds. Preliminary measurements of carbon isotope ratios in Martian organic molecules show values that fall within the range observed for both biological and abiological processes, making definitive interpretations impossible without additional isotopic and molecular data that exceed the analytical capabilities of current robotic missions. The preservation of organic molecules within Martian rocks requires specific geochemical conditions that protect carbon-based compounds from oxidation and thermal decomposition over billions of years. The presence of reducing minerals like pyrite and magnetite within organic-bearing rocks suggests that ancient Martian sediments maintained low oxygen fugacity that prevented organic oxidation. Additionally, the incorporation of organic molecules within clay mineral structures and carbonate cements may provide physical protection against degradation processes, creating microenvironments where organic compounds can survive geological timescales intact. Laboratory experiments designed to test organic molecule stability under Martian surface conditions reveal the extraordinary challenges facing organic preservation on the planet's surface. The combination of intense ultraviolet radiation, oxidizing atmospheric chemistry, and perchlorate minerals in Martian soils creates conditions highly destructive to organic compounds. Surface exposure times of only a few million years can completely destroy organic molecules through photochemical oxidation, suggesting that any organic compounds detected in surface rocks must have been protected from direct surface exposure through burial, incorporation within mineral structures, or formation after surface exposure ended. The diversity of organic molecule types detected across different Martian geological environments suggests multiple formation mechanisms operating under various conditions. Simple organic acids and alcohols could form through Fischer-Tropsch synthesis during serpentinization reactions involving water, carbon dioxide, and iron-bearing minerals. More complex aromatic compounds might result from thermal processing of simpler organic precursors during impact heating or hydrothermal circulation. The synthesis of amino acids and other biochemically relevant molecules requires more specific conditions that could indicate either biological activity or specialized abiological chemistry operating in hydrothermal systems. Seasonal variations in methane concentrations detected in Mars's atmosphere add another layer of complexity to understanding the planet's organic chemistry. Methane, the simplest organic molecule, shows concentration fluctuations that correlate with Martian seasons, suggesting active production and destruction processes operating in the planet's contemporary environment. Potential sources include geological processes like serpentinization, decomposition of subsurface organic deposits, or even contemporary biological activity in subsurface environments. The rapid destruction of atmospheric methane by photochemical processes requires continuous replenishment to maintain observed concentrations. The search for organic molecules in Martian samples faces significant contamination challenges that require extraordinary analytical precision to resolve. Spacecraft and rover components contain organic compounds that could potentially contaminate samples during collection and analysis, while terrestrial contamination during meteorite recovery and laboratory handling can mask or mimic indigenous Martian organics. Advanced analytical protocols using isotopic signatures, molecular structures, and spatial distributions help distinguish truly Martian organic compounds from various contamination sources. But definitive identification often requires multiple independent analytical techniques. The implications of organic molecules in Martian rocks extend far beyond the question of past life on Mars to fundamental understanding of carbon chemistry throughout the solar system. Organic compounds appear to be common components of planetary materials, forming through various geological and possibly biological processes operating under diverse environmental conditions. The detection of organic molecules on Mars, Europa, Enceladus, and Titan suggests that carbon chemistry represents a fundamental aspect of planetary evolution that operates wherever appropriate chemical and physical conditions exist. Future sample return missions will revolutionize understanding of Martian organic chemistry by providing carefully preserved specimens for analysis using the most sophisticated terrestrial analytical instruments. Mass spectrometry techniques capable of determining molecular structures and isotopic compositions with unprecedented precision will decode the complete story preserved within Martian organic molecules. These analyses will determine whether Mars's organic compounds represent chemical fossils of ancient biological activity, products of complex abiological chemistry, or perhaps evidence for contemporary biological processes operating in the planet's subsurface environments. The mystery embedded within Martian organic molecules lies not in their existence, which appears to be common throughout the solar system, but in their significance for understanding the relationship between chemistry and life in planetary environments. Whether these carbon-based compounds represent stepping stones toward biological complexity, chemical fossils of extinct ecosystems, or simply the inevitable products of geological carbon chemistry operating under reducing conditions, remains one of the most profound questions facing planetary science. The answer will reshape understanding of life's prevalence and the chemical pathways that lead from simple molecules toward biological complexity across the cosmos. Atmospheric archaeology reveals itself through gases trapped within crystal defects and mineral boundaries, like microscopic time capsules that preserve samples of ancient Martian skies with meticulous fidelity. These molecular prisoners, captured during mineral crystallization events billions of years ago, carry isotopic fingerprints and chemical compositions that document the evolution of planetary atmospheres across geological time with extraordinary precision. Each trapped gas bubble represents a direct sample of the atmospheric conditions that existed when molten rock cooled into solid mineral structures, creating a geological record of atmospheric evolution that spans the entire history of planetary development, from primordial volcanic outgassing through contemporary thin atmosphere stability. The noble gases provide the most reliable atmospheric archives due to their chemical inertness, which prevents them from reacting with surrounding minerals or being altered by subsequent geological processes. Argon, xenon, krypton, and neon trapped within Martian minerals preserve isotopic ratios that reflect the planet's atmospheric composition during specific epochs of geological history. The ratio of argon-40 to argon-36 in trapped gas samples documents the accumulation of radiogenic argon produced by potassium decay within Mars' interior, providing quantitative measurements of how volcanic outgassing has contributed to atmospheric evolution over billions of years. Comparative analysis of noble gas compositions between Earth and Mars reveals fundamental differences in atmospheric evolution pathways despite similar initial conditions during planetary formation. Martian trapped gases show isotopic signatures indicating substantial atmospheric loss to space, with lighter isotopes preferentially removed through atmospheric escape processes. Earth's trapped noble gases preserve isotopic ratios closer to primordial solar system values, indicating more effective atmospheric retention due to stronger gravitational binding and magnetic field protection. These isotopic differences provide quantitative constraints on atmospheric escape rates and total atmospheric inventories lost by each planet over geological time. The xenon isotope paradox in Martian atmospheric samples creates one of the most intriguing puzzles in comparative planetology. Modern Mars' atmosphere shows xenon isotope ratios that are dramatically different from meteoritic and solar values, indicating that the planet has lost approximately 99% of its original xenon inventory through atmospheric escape. However, xenon's high atomic mass should make it relatively resistant to escape processes, suggesting that Mars experienced more extreme atmospheric loss conditions than simple thermal escape models predict. This xenon depletion may require catastrophic atmospheric loss events or enhanced escape mechanisms operating during periods of intense solar activity. Carbon dioxide isotope ratios preserved in carbonate minerals and trapped gas inclusions document the evolution of Mars's primary atmospheric constituent over geological time. The ratio of carbon-13 to carbon-12 in ancient trapped CO2 differs significantly from modern atmospheric values, indicating that isotopic fractionation has occurred during atmospheric escape, carbonate precipitation, or exchange with subsurface carbon reservoirs. These isotopic variations provide insights into the carbon cycle operating on ancient Mars, including the role of atmospheric CO2 in maintaining greenhouse warming during the planet's early climatic history. Sulfur-bearing gases trapped within Martian minerals preserve evidence for volcanic outgassing compositions and atmospheric chemistry during periods of active volcanism. Sulfur dioxide, hydrogen sulfide, and other sulfur compounds appear in mineral inclusions associated with volcanic rocks, documenting the atmospheric impact of major volcanic episodes throughout Mars's geological history. The isotopic composition of trapped sulfur gases reveals information about the sulfur cycle operating in Mars' early atmosphere, including interactions between volcanic gases, atmospheric chemistry, and surface mineral formation. Water vapor isotope ratios in trapped gas inclusions provide direct measurements of ancient Martian hydrological cycles and atmospheric humidity levels. The deuterium to hydrogen ratio in ancient trapped water vapor is significantly lower than modern Martian atmospheric water, confirming that Mars has lost most of its original water inventory to space through atmospheric escape. These measurements allow scientists to calculate the total amount of water that once existed in Mars' atmosphere and on its surface, providing quantitative constraints on the planet's early habitability and climate evolution. Methane concentrations in ancient trapped gases offer insights into early Martian atmospheric chemistry and potential biological or geological methane production. While methane has not been definitively detected in ancient gas inclusions, the sensitivity limits of current analytical techniques cannot rule out low-level methane concentrations that would indicate active geological or biological processes during Mars's early history. Future analytical improvements may reveal methane signatures that provide crucial information about early Martian habitability and the potential for past biological activity. The spatial distribution of trapped gases across different Martian geological terrains reveals regional variations in atmospheric composition and evolution. Volcanic regions show trapped gas compositions dominated by magmatic volatiles like CO2, SO2, and water vapor, while sedimentary terrains preserve atmospheric gases that reflect surface-atmosphere interactions during aqueous periods. Impact crater materials contain shocked minerals with trapped gases that document atmospheric compositions during major bombardment events, providing snapshots of atmospheric evolution during catastrophic impact episodes. Laboratory analysis of trapped gases requires sophisticated analytical techniques capable of extracting and measuring minute quantities of ancient atmospheric samples without contamination. Stepped heating experiments gradually release gases from different mineral sites and crystallographic positions, allowing scientists to distinguish between primary magmatic gases and secondary atmospheric gases trapped during later alteration events. Mass spectrometry measurements determine isotopic ratios and molecular compositions with precision sufficient to detect subtle variations in atmospheric evolution over geological timescales. The preservation potential of atmospheric samples within minerals depends on crystallographic structures and subsequent alteration history. Minerals with robust crystal structures like zircon and apatite can preserve trapped gases for billions of years without significant loss or isotopic modification. More fragile minerals, or those exposed to aqueous alteration, may lose or exchange their trapped gas inventories, creating complex patterns of gas preservation that require careful analysis to interpret correctly. Understanding these preservation mechanisms is crucial for reconstructing reliable atmospheric histories from trapped gas measurements. Temperature and pressure conditions during mineral crystallization influence the types and concentrations of gases that become trapped within crystal structures. High-temperature crystallization favors the incorporation of magmatic gases directly from cooling magma, while low-temperature crystallization in the presence of atmospheric gases can trap direct samples of ancient atmospheric compositions. The correlation between crystallization conditions and trapped gas compositions allows scientists to distinguish between different atmospheric components and their relative contributions to ancient atmospheric inventories. Future sample return missions will provide unprecedented opportunities to analyze trapped atmospheric gases using state-of-the-art terrestrial analytical facilities. Advanced mass spectrometry techniques can measure isotopic ratios and trace gas concentrations with precision far exceeding that possible with robotic analytical systems. These detailed measurements will reconstruct complete atmospheric evolution histories, including quantitative estimates of atmospheric loss rates, volcanic outgassing fluxes, and the timing of major transitions in atmospheric composition and climate conditions. The temporal evolution of trapped gas compositions creates a chronological record of atmospheric change that can be correlated with other geological and climatic indicators. Early Noachian samples preserve evidence for thick, potentially reducing atmospheres dominated by volcanic outgassing, while later samples document the transition toward oxidizing, thin atmospheric conditions characteristic of modern Mars. This atmospheric evolution record provides crucial constraints on climate models and habitability assessments for different periods of Martian history. The mystery embedded within Martian atmospheric archaeology lies in reconciling the evidence for early thick atmospheres with the physical mechanisms responsible for atmospheric loss. While trapped gas compositions clearly indicate that Mars once possessed substantially thicker atmospheric inventories, the rates and mechanisms of atmospheric escape remain poorly constrained by available data. Understanding how Mars transitioned from early thick atmospheres to contemporary thin atmospheric conditions requires integrating trapped gas evidence with models of atmospheric escape, magnetic field evolution, and solar activity over geological timescales. Impact scars as history books spread across Mars's ancient highlands like a vast library of cosmic violence, each crater preserving the precise timestamp and energy signature of asteroid collisions that shaped both worlds during the solar system's chaotic youth. The late heavy bombardment, occurring approximately 9 billion years ago, left permanent records in the surfaces of terrestrial planets as massive asteroids and comets rained down with devastating frequency, creating impact basins hundreds of kilometers in diameter and excavating billions of tons of crustal material with each collision. Mars, lacking the geological processes that continuously resurface Earth's crust, maintains this impact record in pristine condition, creating a readable chronicle of early solar system dynamics that has been largely erased from Earth's more active surface. The largest impact structures on Mars, including the Hellas Basin stretching 2,300 kilometers across the planet's southern hemisphere, document catastrophic collisions that fundamentally altered planetary evolution and atmospheric development. The Hellas impact, generated by an asteroid perhaps 200 kilometers in diameter, traveling at cosmic velocities exceeding 20 kilometers per second, created a basin so deep that atmospheric pressure at its bottom exceeds the triple point of water during Martian summer conditions. This single impact event excavated crustal material equivalent to the entire volume of Earth's Mediterranean Sea, distributing shock-melted rock and impact breccias across thousands of kilometers and creating secondary crater chains that extend halfway around the planet. Crater size frequency distributions across Mars's surface provide quantitative measurements of bombardment intensity and temporal variations during different epochs of solar system history. The ancient highlands show crater densities approaching saturation equilibrium, where new impacts destroy existing craters at approximately the same rate they create new ones, indicating sustained bombardment over hundreds of millions of years. Younger volcanic plains show progressively lower crater densities that document the exponential decline in bombardment rates following the late heavy bombardment, creating a statistical chronometer that allows scientists to determine absolute ages of Martian surface units with precision comparable to radiometric dating techniques. The morphology and preservation state of Martian impact craters reveal information about surface conditions and atmospheric density during different periods of the planet's history. Fresh craters with sharp rim crests and pristine ejecta blankets formed under current thin atmospheric conditions, while degraded craters with subdued topography and eroded rim materials formed when Mars possessed a thicker atmosphere capable of supporting more intensive erosional processes. The transition between fresh and degraded crater populations marks the epoch when Mars's atmosphere thinned below the threshold necessary for effective wind and possibly water erosion, providing geological evidence for atmospheric evolution that complements isotopic measurements from trapped gases and mineral inclusions. Multi-ring impact basins on Mars preserve structural details that reveal crustal thickness and internal structure during the bombardment epoch. The Utopia Basin, Chryse Basin, and other large impact structures show concentric ring patterns that formed during the complex collapse and rebound processes following massive impact events. The spacing and number of these concentric rings depend on crustal thickness and the strength properties of target materials, allowing scientists to reconstruct Mars' early crustal structure and mechanical properties. These measurements indicate that Mars's early crust was thinner and possibly more fractured than Earth's contemporary continental crust, reflecting differences in planetary size and internal heat generation. Impact-generated hydrothermal systems associated with large Martian craters created localized environments where liquid water could persist for thousands of years after impact events, even during periods when surface conditions were generally hostile to liquid water stability. The heat generated by impact processes can maintain subsurface temperatures above the freezing point of water for millennia, creating temporary habitable environments in crater floors and rim materials. Clay minerals and hydrated sulfates found in association with impact structures provide mineralogical evidence for these post-impact hydrothermal systems, suggesting that impact craters may have served as oases for potential biological activity during Mars's transition from habitable to sterile surface conditions. The composition of impact melt rocks and shock metamorphosed materials within Martian craters preserves information about crustal composition and impact processes that operated during planetary bombardment. Shock metamorphism creates unique mineral assemblages and textural features that form only under the extreme pressure and temperature conditions generated during hypervelocity impacts. Mascalinite, a diaplectic glass formed by shock transformation of plagioclase feldspar, appears in Martian meteorites that originated from impact structures, providing direct samples of shock-processed Martian crustal materials that document impact conditions and target rock compositions. Central peak complexes within large Martian craters expose deep crustal materials that were uplifted from depths of several kilometers during impact crater formation. These central uplifts provide natural drill holes through Mars's crust, exposing rock types and mineral assemblages that formed under high-pressure conditions deep within the planet's interior. Spectroscopic analysis of central peak materials reveals the presence of high-pressure minerals, like olivine and pyroxene, that originated from crustal depths normally inaccessible to surface observations, creating windows into Mars' deep crustal composition and structure. Secondary crater chains radiating from large primary impact structures document the ballistic trajectories and impact velocities of ejector blocks launched during major impact events. These secondary craters, formed by chunks of target material hurled hundreds of kilometers from primary impact sites, preserve information about impact geometry, projectile characteristics, and atmospheric density during impact events. The range and distribution of secondary craters depend on atmospheric drag, which affects the trajectories of high-velocity ejector blocks, providing additional constraints on atmospheric evolution during the bombardment epoch. Comparative analysis of impact crater populations on Earth and Mars reveals fundamental differences in crater preservation and surface evolution processes between the two planets. Earth's active plate tectonics, erosion, and sedimentation have obliterated most impact structures older than a few 100 million years, preserving only about 200 confirmed impact craters from the planet's 4.5 billion year impact history. Mars preserves tens of thousands of impact craters spanning the entire history of solar system bombardment, creating a complete impact record that documents bombardment variations and projectile populations throughout geological time. The relationship between impact cratering and volcanic activity on Mars reveals complex interactions between bombardment processes and internal geological evolution. Large impact basins like Hellas and Utopia may have triggered antipodal volcanic activity through seismic focusing of impact-generated shock waves, creating volcanic provinces on the opposite side of the planet from major impact structures. The Tharsis volcanic region, located approximately antipodal to the Hellas basin, may represent this type of impact-triggered volcanism, suggesting that bombardment processes influenced Mars' internal evolution and surface geology in ways that extended far beyond the immediate impact sites. Atmospheric effects of major impact events on Mars include temporary thickening of the atmosphere through impact vaporization of volatile rich crustal materials and possible triggering of volcanic outgassing through impact-induced fracturing and decompression melting. Large impacts can inject substantial quantities of water vapor, carbon dioxide, and other volatiles into the atmosphere, creating temporary greenhouse warming that could temporarily restore liquid water stability on the planet's surface. These episodic atmospheric thickening events may have extended Mars's habitable period through multiple brief intervals of improved surface conditions. The timing of the late heavy bombardment's end, approximately 3.8 billion years ago, coincides with the transition from Mars' early potentially habitable period to increasingly arid surface conditions. This temporal correlation suggests that bombardment processes may have played crucial roles in maintaining early atmospheric inventories and surface water stability through impact-generated atmospheric thickening and hydrothermal activity. The cessation of intense bombardment removed these episodic sources of atmospheric renewal, allowing gradual atmospheric escape processes to thin Mars' atmosphere below the threshold for surface water stability. Impact crater statistics provide the foundation for absolute age dating of Martian surface units and geological events, creating a chronological framework that allows scientists to correlate surface features with atmospheric evolution, climate change, and potential habitability windows. The crater chronology function, calibrated using lunar samples and theoretical bombardment models, converts crater density measurements into absolute surface ages that can be compared directly with radiometric ages from Martian meteorites and eventually returned samples. The mystery preserved within Mars's impact record lies in understanding how bombardment processes influenced planetary evolution beyond simple surface modification. Impact events may have triggered or terminated geological processes, influenced atmospheric evolution, created temporary habitable environments, and shaped the distribution of volatiles and organic materials across planetary surfaces. Deciphering these complex relationships between bombardment and planetary evolution requires integrating impact crater observations with atmospheric modeling, geological analysis, and eventually detailed laboratory study of impact-processed materials returned from carefully selected crater sites. The sample return journey stretches across interplanetary distances like a cosmic relay race spanning decades, where robotic precision must orchestrate a ballet of orbital mechanics, atmospheric entry, and rocket propulsion to carry precious fragments of Mars back to Earth after their 4.5 billion-year separation. This unprecedented technological endeavor requires 3 separate spacecraft working in perfect coordination across the vast emptiness between worlds, a fetch rover to collect Perseverance's cached samples, an ascent vehicle to launch them into Martian orbit, and an Earth return orbiter to capture the sample container and transport it safely across 300 million kilometers of interplanetary space during the 26-month journey home. The Mars sample return campaign begins with the most sophisticated robotic operation ever attempted on another planet's surface. As the sample retrieval lander deploys both a fetch rover and a rocket system onto the floor of Jezero Crater with landing accuracy measured in hundreds of meters, the fetch rover, equipped with a robotic arm designed specifically for sample container retrieval, must navigate across kilometers of ancient lakebed terrain to locate and collect up to 43 sample tubes that Perseverance has deposited at predetermined coordinates across the crater floor. Each sample container weighs approximately 15 grams and measures 13 centimeters in length, requiring robotic handling precision that can manipulate objects the size of laboratory test tubes while wearing the equivalent of heavy winter gloves. The Mars Ascent Vehicle represents the first rocket ever launched from another planet's surface, designed to operate under atmospheric conditions and gravitational constraints that have never before challenged spacecraft engineers. Mars's thin carbon dioxide atmosphere provides minimal aerodynamic resistance during ascent, while the planet's reduced gravity, 38% of Earth's, allows smaller rocket motors to achieve orbital velocity. However, the extreme temperature variations, dust contamination, and communication delays create engineering challenges that require completely autonomous operation without real-time control from Earth-based mission operators. Orbital rendezvous between the ascending sample container and the waiting Earth return orbiter demands navigation precision measured in meters across the emptiness of Martian orbit, where the slightest error in timing or trajectory could scatter irreplaceable scientific samples across interplanetary space forever. The sample container, no larger than a basketball, must be captured by the orbiting spacecraft using robotic systems that operate with millimeter-level accuracy, while both vehicles travel at orbital velocities exceeding 3 kilometers per second. This cosmic catching operation occurs approximately 300 kilometers above Mars's surface, far beyond any possibility of human intervention if mechanical systems fail to perform their programmed sequences. The Earth return trajectory requires precise calculation of launch windows that align Mars and Earth orbital positions for minimum energy transfer and maximum mission reliability. These interplanetary launch opportunities occur approximately every 26 months when planetary orbital mechanics create favorable geometry for spacecraft traveling between the two worlds. Mission planners must balance trajectory optimization with sample preservation requirements, selecting flight paths that minimize radiation exposure and mechanical stress while ensuring timely delivery to terrestrial laboratories equipped for extraterrestrial sample analysis. Planetary protection protocols governing sample return operations reflect both the extraordinary scientific value of Martian specimens and the theoretical possibility that they might contain viable extraterrestrial microorganisms. The sample container undergoes hermetic sealing on Mars using redundant containment systems designed to prevent any exchange of material between Martian samples and the terrestrial environment during transport and initial laboratory analysis. These protocols, developed through decades of international cooperation and scientific consensus, require that returned samples remain isolated from Earth's biosphere until comprehensive biological and chemical analysis confirms their safety for broader scientific study. The entry, descent, and landing sequence that delivers Martian samples to Earth represents the reverse of Mars mission operations, requiring atmospheric entry at interplanetary velocities exceeding 12 kilometers per second while protecting sample integrity through extreme deceleration forces and thermal heating. The sample return capsule, similar in design to systems that have returned lunar samples and comet particles, employs heat shields and parachute systems to reduce landing speeds to levels that preserve delicate mineral structures and organic compounds within the samples. Landing site selection prioritizes remote locations where sample recovery can proceed under controlled conditions without risk of terrestrial contamination. Sample curation facilities specifically designed for extraterrestrial materials provide the infrastructure necessary for initial characterization and long-term preservation of returned Martian specimens. These laboratories, operating under strict contamination control and planetary protection protocols, employ specialized analytical instruments and sample handling procedures that prevent cross-contamination between different samples while preserving their original chemical and isotopic compositions. The curation process includes comprehensive documentation of sample handling history, analytical measurements, and subsample allocation to ensure that future scientific investigations can interpret results within proper context. International collaboration shapes every aspect of sample return operations, from mission planning and spacecraft development through sample analysis and data distribution. Multiple space agencies contribute technological capabilities, financial resources, and scientific expertise to this unprecedented endeavor, creating a global partnership that reflects the universal significance of comparative planetary science. Sample sharing agreements ensure that Martian specimens will be available to qualified research institutions worldwide, maximizing the scientific return from this extraordinary investment in robotic exploration technology. The analytical capabilities awaiting returned Martian samples exceed those of any robotic mission by several orders of magnitude in sensitivity, precision, and range of measurements possible. Terrestrial laboratories equipped with advanced mass spectrometers, electron microscopes, and synchrotron radiation sources can determine isotopic compositions at the level of individual mineral grains, identify organic compounds at part per billion concentrations, and characterize crystal structures with atomic scale resolution. These analytical capabilities will reveal details about Martian geological processes, atmospheric evolution, and potential biological signatures that remain far beyond the reach of even the most sophisticated robotic analytical systems. The timeline from sample collection to scientific publication spans approximately a decade, including mission development, interplanetary crews, sample analysis, and peer review of scientific results. Initial sample characterization will begin within months of sample return, focusing on basic mineralogical and chemical properties that guide detailed analytical campaigns. Comprehensive isotopic analysis, organic compound identification, and potential biological investigation may require years of careful study using multiple analytical techniques and independent verification by different research groups. Risk mitigation strategies address the numerous failure modes that could compromise sample return operations at any stage from collection through terrestrial delivery. Redundant systems protect against single-point failures in critical mission components, while operational flexibility allows mission controllers to adapt to unexpected circumstances during multi-year mission timelines. Backup sample collection strategies ensure that some scientific return is possible even if primary systems fail, while multiple sample containers reduce the risk of losing entire sample collections through individual component failures. The scientific legacy of returned Martian samples will extend far beyond immediate analytical results to establish comparative planetology as a quantitative science capable of testing theoretical models of planetary evolution with empirical data from multiple worlds. These samples will provide ground truth for orbital observations, calibration standards for future robotic missions, and reference materials for laboratory experiments investigating planetary processes under controlled conditions. The combination of carefully documented geological context and comprehensive analytical characterization will create scientific resources that support decades of research into fundamental questions about planetary habitability and the potential for life beyond Earth. Future sample return missions to other solar system bodies will build upon technological capabilities and operational procedures developed for Mars sample return, extending comparative planetology to include specimens from asteroids, comets, and the moons of giant planets. The success of interplanetary sample return operations opens possibilities for studying primitive solar system materials, organic compounds from outer solar system environments, and potentially even samples from subsurface oceans where extraterrestrial life might currently exist. The mystery that drives sample return efforts lies not in the technological challenges, which are substantial but solvable through engineering innovation, but in the fundamental questions about planetary evolution and biological potential that can only be answered through direct laboratory analysis of extraterrestrial materials. Whether Martian samples will reveal chemical fossils of ancient life, complex organic chemistry operating under alien conditions, or simply elegant geological processes producing familiar mineral assemblages under unfamiliar circumstances remains unknown until these precious fragments of another world finally reach terrestrial laboratories equipped to decode their billion-year-old secrets. Laboratory revelations await in sterile chambers where Earth's most sophisticated analytical instruments prepare to decode the chemical hieroglyphs preserved within Martian stone across billions of years of interplanetary silence. These terrestrial facilities, equipped with mass spectrometers capable of measuring isotopic ratios at the level of individual atoms and electron microscopes that reveal crystal structures with sub-nanometer resolution, represent the culmination of centuries of scientific instrument development focused on extracting maximum information from precious geological specimens. When Martian samples finally arrive in these laboratories after their multi-year journey through space, they will encounter analytical capabilities that exceed those of any robotic mission by factors of thousands in sensitivity, precision, and the range of measurements possible. The sample allocation process begins with comprehensive documentation and initial characterization that catalogs every fragment while preserving the majority of each specimen for future analytical campaigns that may employ techniques not yet invented. Initial examination using non-destructive methods including high-resolution X-ray computed tomography creates three-dimensional maps of internal structures, mineral distributions, and textural relationships without consuming any sample material. These digital archives preserve complete structural information even as subsequent destructive analysis gradually consumes portions of each specimen, ensuring that future researchers can reconstruct original sample characteristics decades after initial analysis campaigns conclude. Secondary ion mass spectrometry, operating at the forefront of analytical chemistry, can determine isotopic compositions and trace element concentrations within individual mineral grains, measuring only micrometers in diameter. This technique bombards samples with focused ion beams that sputter individual atoms from target surfaces, allowing mass spectrometric analysis of isotopic ratios with precision sufficient to detect variations of parts per thousand in isotopic composition. Applied to Martian samples, this analytical approach will reveal isotopic signatures of atmospheric evolution, hydrothermal alteration, and potentially biological fractionation processes that operated during Mars's early history. Synchrotron radiation facilities provide X-ray beams billions of times brighter than conventional laboratory sources, enabling crystallographic analysis and chemical mapping at spatial resolutions approaching atomic dimensions. These particle accelerator-based light sources can identify mineral phases present in quantities too small for conventional analytical techniques while determining their crystal structures and chemical compositions with unprecedented precision. Martian samples analyzed using synchrotron techniques will reveal mineral assemblages and chemical zoning patterns that document formation conditions, alteration processes, and thermal histories with detail impossible to achieve through robotic analytical systems. Organic compound analysis employs the most sensitive chemical analytical techniques available to terrestrial science, capable of identifying individual organic molecules at concentrations measured in parts per trillion while determining their molecular structures and isotopic compositions. Gas chromatography mass spectrometry systems equipped with multidimensional separation capabilities can resolve complex mixtures of organic compounds and distinguish between different structural isomers that may indicate biological versus abiological formation mechanisms. These analytical capabilities will determine whether Martian organic compounds represent chemical fossils of ancient biological activity or products of purely geological carbon chemistry. Electron microscopy techniques reveal structural details of Martian minerals at magnifications exceeding 1 million times, documenting crystal defects, chemical zoning, and textural relationships that preserve information about formation and alteration processes. Transmission electron microscopy can resolve individual crystal lattice planes and atomic scale features within mineral structures, while scanning electron microscopy provides high-resolution images of surface textures and compositional variations. These microscopic observations will reveal evidence for biological processes, impact metamorphism, hydrothermal alteration, and other geological processes that shaped Martian rocks over billions of years. Noble gas mass spectrometry operating in stepped heating mode can extract and analyze atmospheric gases trapped within individual mineral grains during crystallization events spanning Mars's geological history. This technique gradually releases trapped gases by incrementally heating samples to progressively higher temperatures, allowing scientists to distinguish between different gas reservoirs and determine their isotopic compositions and relative abundances. The resulting data will reconstruct Mars's atmospheric evolution with quantitative precision, documenting atmospheric loss rates, volcanic outgassing compositions, and climate change over geological timescales. Radiometric age dating using multiple isotopic systems will determine precise crystallization ages for Martian minerals while documenting subsequent thermal events that affected sample cooling and alteration histories. Uranium lead dating of zircon crystals can determine ages with precision of millions of years for samples billions of years old, while rubidium, strontium, and potassium-argon systems provide complementary age information for different mineral phases. These geochronological measurements will establish absolute timescales for Martian geological processes and correlate sample formation ages with orbital observations of geological units and impact crater chronologies. Magnetic property measurements reveal information about ancient Martian magnetic fields preserved within iron-bearing minerals that recorded magnetic field directions and intensities during crystallization. Paleomagnetic analysis can determine whether samples formed during periods when Mars possessed a global magnetic field while documenting field strength variations and reversal patterns. These measurements will provide ground truth for orbital magnetic anomaly observations and constrain models of Mars' magnetic dynamo evolution and its relationship to atmospheric retention and climate stability. Sample preparation techniques developed specifically for extraterrestrial materials ensure that analytical measurements reflect original Martian compositions rather than terrestrial contamination or laboratory artifacts. Ultra-clean sample handling procedures employ specialized tools and environments that prevent introduction of terrestrial organic compounds, water, or other contaminants that could interfere with measurements of indigenous Martian materials. Ion beam milling and focused ion beam techniques prepare samples for analysis while minimizing damage to delicate structures and preserving original chemical signatures. Collaborative analytical campaigns involving multiple laboratories and research institutions maximize scientific return while providing independent verification of critical measurements. Different analytical techniques applied to subsamples from the same specimens allow comprehensive characterization while cross-validating results obtained using different analytical approaches. International sample sharing ensures that the most qualified research groups worldwide can contribute specialized analytical capabilities to address specific scientific questions about Martian geological processes and potential biological signatures. Advanced analytical protocols specifically designed for searching for biosignatures employ multiple independent techniques to distinguish between biological and abiological processes that could produce similar chemical signatures. Amino acid enantiomer ratios, stable isotope fractionation patterns, and organic compound distributions provide multiple lines of evidence that must be consistent with biological processes before definitive biological interpretations can be supported. These rigorous analytical standards reflect lessons learned from previous controversial claims about extraterrestrial life and ensure that any positive biosignature detections meet the highest standards of scientific evidence. Quality control and interlaboratory comparison programs validate analytical accuracy and precision while ensuring that measurements from different laboratories can be directly compared and combined. Standard reference materials with known compositions allow calibration of analytical instruments and assessment of measurement uncertainties, while round-robin analytical exercises identify systematic biases and improve analytical protocols. These quality assurance measures ensure that scientific conclusions based on Martian sample analysis will withstand rigorous peer review and independent verification. Long-term sample preservation strategies balance current analytical requirements with the need to preserve substantial portions of each sample for future analytical campaigns using techniques not yet developed. Sample storage under controlled atmospheric conditions prevents oxidation and contamination while maintaining original chemical and isotopic compositions indefinitely. Reserved portions of each sample create opportunities for future generations of scientists to address new questions using analytical capabilities that may exceed current techniques by orders of magnitude. The analytical timeline extends across multiple years as different research groups address complementary aspects of Martian geological processes using specialized techniques optimized for specific types of measurements. Initial characterization, focusing on basic mineralogical and chemical properties, guides more detailed analytical campaigns that may require months or years of careful measurement and data interpretation. Comprehensive analysis of complex samples may continue for decades as new analytical techniques become available and new scientific questions emerge from initial results. Database development and data management systems ensure that analytical results from multiple laboratories and research institutions can be integrated and compared while maintaining complete documentation of analytical procedures and measurement uncertainties. These databases will serve as permanent scientific resources that support ongoing research long after initial analytical campaigns conclude, enabling future meta-analyses and reinterpretation of results as scientific understanding advances. The mystery that awaits resolution in terrestrial laboratories lies not in the analytical capabilities themselves, which are well established and continuously improving, but in the fundamental questions about planetary evolution and biological potential that Martian samples may answer or transform entirely. Whether these carefully preserved fragments of another world will confirm current understanding of planetary processes or reveal unexpected phenomena that require new theoretical frameworks remains unknown until the most sensitive analytical instruments on Earth finally examine materials that formed under alien skies billions of years ago. Comparative planetology's promise unfolds through the mathematical precision of physical laws that govern atmospheric evolution, revealing how Mars's geological death illuminates the delicate mechanisms that maintain Earth's continued habitability across billions of years of cosmic time. By studying the processes that transformed Mars from a warm, wet world capable of supporting liquid water into the cold, arid planet observed today, scientists develop quantitative models of atmospheric loss, magnetic field evolution, and climate stability that can be applied to predict Earth's own atmospheric and geological future under changing solar and internal conditions. This comparative approach transforms planetary science from descriptive observation into predictive understanding, creating theoretical frameworks that explain why some worlds maintain habitable conditions while others evolve towards sterility despite similar initial endowments. The fundamental physics of atmospheric escape operates identically on both worlds, but planetary mass and magnetic field strength determine which atmospheric constituents remain gravitationally bound over geological timescales. Mars's weaker gravitational field allows atmospheric molecules to achieve escape velocity more easily than on Earth, while the loss of magnetic protection exposes the atmosphere to direct solar wind erosion that strips away gases molecule by molecule across millions of years. These same processes operate on Earth, but at rates reduced by factors of hundreds due to stronger gravitational binding and continuous magnetic field protection, suggesting that Earth's atmospheric stability depends on maintaining these protective mechanisms over geological time. Solar evolution models predict that the Sun's luminosity will increase by approximately 10% over the next billion years as hydrogen fusion gradually changes the stellar core composition and internal structure. This brightening will increase Earth's surface temperature by several degrees Celsius, potentially triggering positive feedback mechanisms that accelerate water vapor accumulation in the atmosphere and enhance greenhouse warming. Mars's atmospheric evolution provides a natural experiment for understanding how planetary atmospheres respond to changing stellar radiation, offering insights into the climate stability mechanisms that will determine Earth's habitability as solar luminosity continues to increase. The carbonate-silicate cycle that regulates Earth's atmospheric carbon dioxide concentration and surface temperature operates through interactions between atmospheric chemistry, surface weathering, and plate tectonic processes that recycle carbon between surface and interior reservoirs. Mars's lack of active plate tectonics prevented this regulatory mechanism from operating effectively, allowing atmospheric carbon dioxide to accumulate in surface deposits or escape to space without replenishment through volcanic outgassing. Understanding why this crucial climate regulation system failed on Mars reveals the geological prerequisites for maintaining stable surface temperatures over billions of years, including the importance of planetary size in sustaining internal heat and tectonic activity. Magnetic field evolution depends on complex interactions between planetary size, core composition, and heat generation rates that determine whether dynamo processes can operate continuously over geological timescales. Earth's larger core and higher internal heat production maintain vigorous convective motion that sustains magnetic field generation, while Mars's smaller size allowed core cooling and eventual dynamo shutdown approximately 4 billion years ago. Theoretical models of magnetic field evolution suggest that Earth's dynamo will continue operating for several billion years into the future, but eventual core cooling will terminate magnetic protection and expose the atmosphere to enhanced escape processes similar to those that transformed Mars. Atmospheric modeling studies that successfully reproduce Mars's observed atmospheric evolution and isotopic compositions provide validated theoretical frameworks for predicting how Earth's atmosphere will respond to future changes in solar radiation. Magnetic field strength and internal heat generation. These models incorporate the complex physics of atmospheric escape, including thermal escape, ion pickup, and hydrodynamic blow-off, while accounting for the protective effects of magnetic fields and gravitational binding. Applied to Earth's future evolution, these models suggest that atmospheric loss will remain negligible for billions of years under current conditions, but could accelerate significantly if magnetic field protection weakens or solar activity increases. The timing relationships between atmospheric evolution, magnetic field history, and geological activity on Mars provide crucial constraints on the sequence of events that determine planetary habitability over geological timescales. Mars lost its magnetic field approximately 4.1 billion years ago, followed by gradual atmospheric thinning and the cessation of widespread surface water activity by 3.5 billion years ago. This temporal progression suggests that magnetic field loss precedes and potentially triggers atmospheric evolution and climate change, indicating that Earth's magnetic field stability represents a crucial factor in maintaining long-term habitability. Isotopic evidence from Martian atmospheric evolution, preserved in meteorites and surface materials, documents quantitative relationships between magnetic field strength, atmospheric escape rates, and isotopic fractionation that can be applied to monitor Earth's atmospheric stability over geological time. The progressive enrichment of heavy isotopes in Mars's residual atmosphere provides a sensitive indicator of atmospheric loss processes, while isotopic compositions of ancient trapped gases document atmospheric conditions before escape became dominant. Similar isotopic monitoring of Earth's atmospheric evolution could provide early warning of changes in atmospheric stability long before effects become apparent through other observations. Comparative studies of water loss mechanisms reveal fundamental differences between Mars and Earth that illuminate the factors controlling long-term water retention on planetary surfaces. Mars has lost approximately 85% of its original water inventory through atmospheric escape processes, while Earth has retained most of its water despite receiving similar solar radiation over geological time. The key difference lies in Earth's stronger magnetic field protection and more efficient water recycling through plate tectonic processes that return water to the interior through subduction and release it through volcanic outgassing. maintaining a stable hydrological cycle over billions of years. Climate sensitivity studies using Mars as a natural laboratory for extreme climate change reveal the non-linear relationships between atmospheric composition, surface temperature, and feedback mechanisms that could affect Earth's future climate stability. Mars's transition from early warm, wet conditions to current cold, dry climate occurred through a cascade of positive feedback processes that accelerated atmospheric loss and cooling once critical thresholds were exceeded. Understanding these threshold effects and tipping points provides insights into Earth's climate system stability and the conditions under which irreversible climate change could occur despite human mitigation efforts. Geological analog studies comparing Martian and terrestrial mineral assemblages, sedimentary processes, and hydrothermal systems reveal fundamental similarities in planetary geological processes despite different environmental conditions. Both worlds show evidence for similar igneous differentiation, aqueous alteration, and impact modification processes, suggesting that basic geological principles operate universally across different planetary environments. These similarities validate the use of terrestrial geological understanding to interpret Martian observations while highlighting the environmental factors that determine which geological processes dominate planetary evolution. The preservation potential of geological and potentially biological records depends on planetary conditions that affect the stability of surface materials over geological timescales. Mars's geological quiescence has preserved surface features and mineral assemblages for billions of years, creating an archive of early planetary conditions that has been largely destroyed on Earth through plate tectonic recycling and erosion. This preservation differential suggests that ancient Earth may have experienced environmental conditions and geological processes similar to those preserved on Mars, but evidence has been destroyed through Earth's more active geological evolution. Astrobiology implications of Mars's atmospheric evolution extend beyond understanding past habitability to predicting the long-term survival prospects for life on Earth and other potentially habitable worlds. The mechanisms that terminated Mars's habitability operate on Earth as well, but at greatly reduced rates due to planetary mass and magnetic protection effects. Understanding the timescales and triggers for these processes provides insights into the duration of habitable conditions on Earth and the factors that determine whether life can evolve and persist on other worlds throughout the galaxy. Planetary protection considerations for Earth's future require understanding how atmospheric evolution, magnetic field changes, and climate instability could affect the biosphere over geological and astronomical timescales. While human activities currently dominate short-term environmental change, long-term planetary evolution will ultimately determine the survival prospects for terrestrial life regardless of human technological capabilities. Mars's atmospheric evolution provides quantitative models for these long-term processes, enabling assessment of natural threats to Earth's habitability that operate on timescales far longer than human civilization. Technological implications of comparative planetology research include the development of planetary engineering concepts that could potentially modify atmospheric evolution and extend habitable conditions on Earth or other worlds. Understanding the mechanisms that terminated Mars's habitability suggests possible interventions that could maintain or restore atmospheric stability, including artificial magnetic field generation, atmospheric replenishment, and climate regulation technologies. While such planetary-scale engineering remains far beyond current capabilities, comparative planetology research provides the theoretical foundation for evaluating the feasibility and requirements of such interventions. The mystery embedded within comparative planetology lies not in understanding individual planetary processes, which are increasingly well characterized through observation and modeling, but in predicting the complex interactions and feedback mechanisms that determine long-term planetary habitability under changing conditions. Mars provides one example of how planetary evolution can proceed, but Earth's different mass, composition, and orbital characteristics create unique evolutionary pathways that may lead to different outcomes over similar timescales. Whether Earth's geological and atmospheric systems possess sufficient stability and regulatory capacity to maintain habitable conditions indefinitely, or whether similar processes will eventually transform Earth toward Mars-like conditions, remains one of the most profound questions facing planetary science and human civilization. Two worlds. One story emerges from the patient accumulation of isotopic measurements, mineral compositions, and atmospheric signatures that reveal Mars as Earth's geological Rosetta Stone, translating the universal language of planetary evolution across the vast temporal scales that shape worlds. This comparative narrative transcends the boundaries between individual planets to illuminate fundamental principles of planetary science that operate wherever rocky worlds orbit main-sequence stars, creating predictive frameworks for understanding not only the past and future of our own world, but the evolutionary pathways followed by potentially thousands of terrestrial planets orbiting distant stars throughout the galaxy. The story written in Martian stone speaks to processes that began with stellar nucleosynthesis, continued through planetary accretion, and will persist until stellar evolution transforms the inner solar system billions of years into the future. The isotopic signatures preserved within Martian rocks and Earth's oldest geological formations reveal their shared origin from the same reservoir of materials within the early solar nebula, yet document divergent evolutionary pathways that transformed initially similar worlds into profoundly different planetary environments. Both planets, formed through accretion of planetesimals composed of identical chondritic materials, underwent similar early differentiation processes that separated metallic cores from silicate mantles, and experienced comparable bombardment by asteroids and comets during the solar system's chaotic youth. The fundamental similarity of their initial conditions makes their subsequent evolutionary divergence all the more remarkable and scientifically informative about the factors that determine planetary habitability over geological time. Atmospheric evolution models calibrated using Mars's documented atmospheric loss and Earth's atmospheric retention reveal the mathematical relationships between planetary mass, magnetic field strength, and atmospheric stability that govern long-term climate evolution on terrestrial worlds. These quantitative models demonstrate that planetary habitability depends not only on orbital distance from the host star, but also on internal properties including core composition, heat generation rates, and the timing of magnetic dynamo evolution. Mars serves as a natural experiment that validates theoretical models of atmospheric escape while providing empirical data for predicting atmospheric evolution on Earth and exoplanets with similar characteristics. The geological record preserved on both worlds documents universal processes of igneous differentiation, aqueous alteration, and impact modification that operate according to fundamental physical and chemical principles, regardless of planetary size or atmospheric composition. Volcanic rocks on Mars show mineralogical and chemical characteristics nearly identical to terrestrial basalts, indicating that magma generation and crystallization follow similar pathways on both worlds. Sedimentary rocks formed in ancient Martian lakes preserve depositional structures and chemical signatures that closely parallel those found in terrestrial lacustrine deposits, demonstrating that sedimentary processes operate similarly wherever liquid water interacts with rocky surfaces. Hydrothermal systems documented in Martian geological formations reveal aqueous geochemistry and mineral precipitation processes that mirror those operating in terrestrial hot spring environments, underground aquifers, and mid-ocean ridge systems. The clay minerals, sulfate deposits, and carbonate formations found across Mars's ancient terrains formed through water-rock interactions under temperature and pH conditions comparable to those found in Earth's contemporary hydrothermal environments. This convergent aqueous geochemistry suggests that habitable conditions, characterized by liquid water and moderate temperatures, develop naturally through geological processes operating on terrestrial planets throughout the galaxy. The timing relationships between geological processes, atmospheric evolution, and potential habitability windows provide crucial insights into the factors that determine how long planets can maintain conditions suitable for life. Mars maintained habitable surface conditions for approximately 500 million to 1 billion years before atmospheric loss and cooling terminated widespread liquid water stability, while Earth has sustained habitable conditions for at least 3.8 billion years and will likely continue to do so for billions of years into the future. This dramatic difference in habitability duration reflects the importance of planetary mass and magnetic field stability in maintaining long-term environmental conditions suitable for biological evolution. Organic chemistry documented in Martian samples reveals that carbon-based molecular complexity develops naturally through geological processes operating under reducing conditions in subsurface environments. The detection of amino acids, aromatic hydrocarbons, and other complex organic compounds in Martian rocks demonstrates that the chemical building blocks necessary for biological systems form readily through abiological processes under appropriate conditions. This finding suggests that organic chemistry represents a fundamental aspect of planetary evolution rather than a rare occurrence requiring special circumstances, implying that potentially habitable worlds throughout the galaxy possess the chemical ingredients necessary for life. Impact crater populations preserved on Mars's ancient surface provide a complete record of bombardment intensity and temporal variations during the early solar system's evolution, while Earth's more limited crater record documents only the most recent portion of bombardment history. The combination of Martian and terrestrial crater data reveals bombardment patterns that affected all inner solar system bodies, including periods of intense bombardment that may have influenced the origin and early evolution of life. Understanding bombardment history helps assess the frequency and severity of impact events that could affect biosphere evolution on Earth and other potentially habitable worlds. Magnetic field evolution on both worlds illustrates the crucial role of planetary dynamos in maintaining atmospheric stability and surface habitability over geological timescales. Earth's continuing magnetic field generation protects the atmosphere from solar wind erosion and maintains the magnetosphere that shields the surface from harmful cosmic radiation. Mars's early magnetic field provided similar protection during the planet's potentially habitable epoch, but dynamo shutdown approximately 4 billion years ago initiated atmospheric escape processes that gradually transformed surface conditions. This comparative magnetic history demonstrates the importance of sustaining internal heat generation and core convection for long-term planetary habitability. Climate system evolution reveals the complex feedbacks between atmospheric composition, surface temperature, and geological processes that determine planetary climate stability over billions of years. Earth's carbonate-silicate cycle, enabled by plate tectonics and continental weathering, provides a thermostat mechanism that regulates atmospheric carbon dioxide concentrations and surface temperatures despite variations in solar luminosity and volcanic outgassing. Mars lacked this regulatory mechanism due to its smaller size and limited tectonic activity, allowing climate to evolve without stabilizing feedbacks and eventually reaching a stable but uninhabitable equilibrium. Sample return missions create unprecedented opportunities for direct laboratory comparison of materials from both worlds using identical analytical techniques and measurement protocols. This comparative approach eliminates systematic biases that might affect interpretation of data obtained using different analytical methods on different planets, while enabling measurements with precision and sensitivity far exceeding that possible with robotic analytical systems. Direct comparison of isotopic compositions, mineral structures, and organic compounds from both worlds will provide definitive tests of theoretical models and reveal subtle differences in planetary processes that cannot be detected through orbital observations or meteorite analysis alone. Astrobiology implications extend beyond the search for past or present life on Mars to fundamental understanding of the conditions and processes that determine whether biological systems can originate and evolve on planetary surfaces. The documented chemical complexity and potentially habitable conditions that existed on early Mars provide insights into the environmental requirements for biological origin, while demonstrating that such conditions develop naturally through geological processes. Whether life actually originated on Mars remains unknown, but the planet's chemical and environmental evolution illuminates the pathways through which non-biological planetary systems could transition toward biological complexity. Technological applications of comparative planetology research include the development of life detection strategies, planetary protection protocols, and eventually terraforming concepts that could modify planetary environments to enhance habitability. Understanding the processes that terminated Mars's natural habitability suggests possible interventions that could restore or maintain habitable conditions, While comparative studies of atmospheric evolution inform strategies for detecting and characterizing potentially habitable exoplanets, the lessons learned from Mars's atmospheric evolution also provide insights into Earth's climate sensitivity and the long-term consequences of atmospheric modification through natural or anthropogenic processes. Future exploration missions to both worlds will continue expanding the comparative database while testing theoretical models against empirical observations from multiple planetary environments. Robotic missions to Mars focus on understanding ancient environmental conditions and searching for biosignatures, while Earth-based research investigates early terrestrial environments and biological evolution under conditions similar to those that existed on early Mars. This coordinated approach maximizes scientific return while ensuring that discoveries on one world inform exploration strategies and interpretive frameworks for the other. The philosophical implications of Mars as Earth's geological twin transcend scientific understanding to address fundamental questions about planetary habitability, biological potential, and humanity's place in cosmic evolution. If Mars once possessed conditions similar to early Earth, yet failed to develop detectable life, this finding would suggest that biological evolution requires more than suitable environmental conditions. Conversely, if evidence for past Martian life is eventually discovered, this would demonstrate that biological evolution represents a probable outcome of planetary chemical evolution rather than an extraordinary accident unique to Earth. The mystery that unites both worlds lies not in their individual geological histories, which are increasingly well understood through decades of exploration and analysis, but in the fundamental question of whether planetary evolution inevitably leads toward biological complexity under appropriate conditions. Mars and Earth represent two experiments in planetary evolution operating under similar initial conditions but different physical constraints, creating a natural laboratory for testing hypotheses about habitability, climate stability, and the factors that determine whether worlds remain habitable long enough for biological evolution to produce complex ecosystems. The answer to this question will determine whether Earth represents a typical outcome of planetary evolution or an extraordinary exception in a universe where most worlds follow Mars-like evolutionary pathways toward elegant sterility. The samples rest now in their titanium containers, scattered across the ancient floor of Jezero Crater like seeds waiting for harvest, each one carrying the quiet weight of two worlds' intertwined history. 4.5 billion years have passed since iron and silicon first condensed from stellar dust in the same cosmic nursery, forming the building blocks that would become both the red plains of Mars and the blue oceans of Earth. The rocks sleep in Martian twilight, holding their secrets with geological patience, preserving isotopic whispers and mineral memories that remember when both worlds knew flowing water and thick skies. In future years, robotic arms will gather these fragments with mechanical tenderness, loading them into spacecraft that will carry Mars back to Earth across the emptiness between planets. Terrestrial laboratories await with instruments sensitive enough to read the molecular signatures of ancient atmospheres, to decode the chemical stories written in crystal lattices, to distinguish between the organic compounds that hint at life and those that emerge from stone alone. Scientists will measure isotopic ratios with precision that transform speculation into knowledge, revealing whether Mars and Earth shared not only materials and processes, but perhaps the spark of biology itself. The crater sleeps under alien constellations, its lakebed sediments holding answers to questions about planetary evolution, atmospheric loss, and the delicate mechanisms that determine whether worlds remain habitable across the vast scales of cosmic time. Mars has become Earth's teacher, offering lessons in atmospheric escape, magnetic field evolution, and the consequences of planetary size for sustaining the geological processes that maintain habitable conditions. Two worlds that began as twins now stand as testament to the contingent nature of planetary evolution, where slight differences in mass and orbital characteristics cascade across billions of years to create profoundly different outcomes. The night wind stirs Martian dust with the same physics that moves Earth's atmosphere, yet the pressure is too thin, the temperature too cold for liquid water to survive on the surface. Below ground, Ice crystals preserve the memory of rivers that once carved valleys now filled only with silence and stone. In some distant future, when the sun brightens and Earth's own atmosphere begins to change, scientists will remember Mars's story and perhaps find wisdom in the patient testimony of rocks that witnessed the transformation of worlds. The samples wait, carrying their ancient messages forward through time, ready to reveal the universal language of planetary evolution written in elements forged in dying stars and preserved in the patient archives of stone.